From invisible forces shaping galaxies to particles so elusive they can pass through planets without leaving a trace, space is full of surprises that challenge everything we think we know. Let's go on a journey and explore mysterious cosmic structures, dive into the quirks of exotic matter, and discuss the theories that scientists are using to explain it all. Join me as we explore mind-boggling space facts, the largest structures in the universe, discovering galactic superclusters. Galactic superclusters are the largest known structures in the universe, sprawling across hundreds of millions of light-years and containing tens of thousands of galaxies. They are so vast that even light, the fastest thing in the universe, would take hundreds of millions of years to travel from one end of a supercluster to the other. One of the most well-known superclusters is Laniakea, which translates to immeasurable heaven in Hawaiian. It was identified in 2014, and its discovery redefined our understanding of the Milky Way's place in the universe. Laniakea stretches across 520 million light-years and encompasses over 100,000 galaxies, including our own. The Milky Way lies near the edge of this supercluster, nestled within a smaller structure called the Local Group, which itself is part of a larger network of galaxies drawn together by gravity. Galactic superclusters like Laniakea are not randomly distributed across the universe. They are part of the cosmic web, a vast network of filaments made up of galaxies, dark matter, and gas. Between these filaments are enormous voids, regions of space with very few galaxies, where matter is sparse. This web-like structure is thought to have formed after the Big Bang, as gravity pulled matter together, creating dense regions that would eventually give rise to galaxies and clusters. Over billions of years, these clusters grew and merged, forming the massive superclusters we see today. The force of gravity draws galaxies toward one another, pulling them into ever larger groups and structures. At the heart of many superclusters are massive galaxy clusters that act as gravitational anchors, holding smaller groups of galaxies in place. These central clusters are often surrounded by filaments of galaxies that stretch out like cosmic highways, connecting different parts of the supercluster. The study of galactic superclusters has revealed surprising details about the universe's structure and evolution. For instance, scientists have found that galaxies within a supercluster are not stationary. They move, pulled by the combined gravitational forces of nearby galaxies, clusters, and the supercluster as a whole. In Laniakea, for example, the motion of galaxies is influenced by a gravitational center called the Great Attractor. This region, located about 150 million light-years away, is pulling galaxies towards it with immense force, shaping the movement of everything within the supercluster. If the Milky Way were the size of a small coin, Laniakea would cover an area as large as North America. And Laniakea is just one supercluster among many. Beyond it lies an even larger structure called the Shapley supercluster, a very densely packed region that has the largest matter concentration in the local universe. These superclusters are part of a hierarchy of structures that extends up to the cosmic web itself, the largest structure in the universe. Understanding how galactic superclusters form requires looking back to the early universe, when matter was more evenly distributed. Tiny fluctuations in the density of matter eventually grew under the influence of gravity, creating the first seeds of galaxies and clusters. As these structures merged, they formed larger and larger groups, eventually becoming superclusters. The process is ongoing. Superclusters continue to grow and evolve, with galaxies and clusters being drawn closer together over time. Dark matter, the invisible substance that makes up most of the universe's mass, is a key ingredient in the formation of superclusters. Although we cannot see dark matter, its gravitational effects are evident in the way galaxies move and in the structure of the cosmic web. Dark matter provides the scaffolding for superclusters, with its gravitational pull shaping the distribution of visible matter. Without dark matter, the universe as we know it would not exist. The immense scale of galactic superclusters also provides insight into the nature of dark energy, the force driving the accelerated expansion of the universe. While gravity works to pull galaxies together, dark energy pushes them apart, stretching the fabric of space itself. The balance between these two forces determines the fate of superclusters. Over time, as dark energy continues to dominate, galaxies in different superclusters will drift farther apart, eventually becoming isolated in an ever-expanding universe. Observing galactic superclusters is a challenging task, given their size and distance. Astronomers rely on powerful telescopes to map the positions of galaxies and measure their motions. By studying the redshift of light from distant galaxies, how the light stretches as the universe expands, scientists can determine their distances and velocities. These measurements allow researchers to map the large-scale structure of the universe. By modeling the universe's evolution from its early stages to the present day, scientists can test theories about how superclusters form and grow. These simulations incorporate the effects of gravity, dark matter, and dark energy, creating virtual universes that closely resemble the one we observe. Comparing these models to real data helps refine our understanding of the processes that shape the cosmos. Fermi bubbles, the Milky Way's mysterious gamma-ray clouds. Fermi bubbles are among the most spectacular features of the Milky Way galaxy, stretching out like ghostly twin plumes above and below its central region. Discovered in 2010 by scientists analyzing data from the Fermi Gamma Ray Space Telescope, these enormous structures glow faintly in gamma rays, one of the most energetic forms of light. Despite their name, Fermi bubbles are not solid or even gaseous clouds in the traditional sense. They are zones of energized particles interacting with magnetic fields and radiation, creating their unique gamma-ray signature. What makes Fermi bubbles so intriguing is not only their size, spanning some 25,000 light-years, but their location and the unanswered questions about their origins. Positioned symmetrically around the galactic core, these structures seem to be tied to the activity of the supermassive black hole at the heart of the Milky Way. The black hole, known as Sagittarius A*, lies relatively quiet today, showing no signs of the violent outbursts often seen in other galaxies. Yet, the Fermi bubbles suggest a different story, one where dramatic events shaped the core of our galaxy in the distant past. One of the leading hypotheses points to a period of intense activity from Sagittarius A*. Supermassive black holes like this one occasionally experience feeding frenzies, where an influx of gas and dust spirals into their gravitational grasp. As this material accelerates toward the black hole, it heats up to millions of degrees, emitting enormous amounts of energy in the process. Some of this energy gets funneled into powerful jets, which can blast material far into space at nearly the speed of light. It's possible that the Fermi bubbles are the fading remnants of one such episode. Another theory suggests that the bubbles are linked to bursts of star formation. Deep within the galaxy's core, the density of stars is incredibly high. This crowded environment creates ideal conditions for the rapid birth and death of stars. Massive stars in particular live fast and end their lives in spectacular supernova explosions. These explosions release shock waves that push surrounding material outward. If such events occurred frequently over millions of years, they could have created the energy needed to inflate the Fermi bubbles. Observations of the bubble's shape and composition reveal sharp edges, suggesting that the structures formed relatively quickly and have remained intact rather than dissipating into the surrounding galaxy. This sudden formation supports the idea of a singular energetic event, like a black hole outburst, rather than a slower process like ongoing star formation. However, the edges are not entirely smooth. They appear rippled, hinting at turbulence. This turbulence might indicate interactions between the bubbles and other galactic phenomena, such as magnetic fields or high-speed particles, known as cosmic rays. Gamma rays are typically produced in extreme environments, like those involving high-energy collisions or radioactive decay. Within the Fermi bubbles, the leading explanation is that cosmic rays are colliding with interstellar gas. These cosmic rays are thought to have been accelerated by shockwaves from whatever event created the bubbles in the first place. As they travel through the bubbles, the collisions release gamma rays, lighting up these vast structures. The Fermi bubbles also emit X-rays and even some radio waves, suggesting a complex mix of processes at work. The X-rays could point to extremely hot gas within the bubbles, while the radio waves might come from electrons spiraling along magnetic field lines. This combination of emissions allows astronomers to study the bubbles across different wavelengths of light, each revealing new aspects of their composition and behavior. To gain better understanding of the Fermi bubbles, researchers often compare them to similar features in other galaxies. In some active galaxies, scientists have observed massive outflows of gas and radiation being ejected from their cores. These outflows, driven by supermassive black holes, share striking similarities with the Fermi bubbles, including their shape, size, and alignment with the galactic plane. This comparison strengthens the idea that Sagittarius A** once went through a more active phase, potentially millions of years ago, when it might have released jets of energy that carved out the bubbles. Still, there are many unanswered questions. For instance, why do the Fermi bubbles stop at their current size? If they were formed by a black hole outburst or starburst activity, what caused them to halt their expansion? Could there be forces within the Milky Way, like magnetic fields or pressure from interstellar gas, keeping the bubbles contained? Another mystery is the faint haze of microwave radiation observed within the bubbles, known as the microwave haze. This additional emission doesn't neatly fit into existing models and might point to unknown particles or processes at work. By modeling how different energetic events, such as black hole jets or starbursts, would shape the Milky Way, scientists can test their theories against the bubble's actual properties. These simulations often reveal surprising details, like how magnetic fields could channel the outflow of energy or how the bubbles interact with the surrounding galaxy. Each new finding adds another piece to the puzzle, slowly uncovering the history of our galaxy's core. The cosmic horizon problem. Why does the universe look the same everywhere? The universe is a vast and dynamic place, yet when we look out into the cosmos, it appears surprisingly uniform. No matter where we point our telescopes, the temperature of the CMB or the cosmic microwave background, the faint glow of radiation left over from the Big Bang, is almost exactly the same. The density of matter, too, seems remarkably even on large scales, with galaxies and galaxy clusters spread out in patterns that look similar in all directions. This smoothness is both fascinating and puzzling, leading scientists to ask, how did the universe become so uniform, and why does it still look this way? The cosmic horizon problem is rooted in the idea that different parts of the universe should not have been able to communicate with each other in the time since the Big Bang. The universe has a speed limit, the speed of light, and since the universe is only about 13.8 billion years old, light or any information can only have traveled so far. This creates a horizon, beyond which regions of the universe should have no way of influencing each other. Yet when we observe the CMB, we see that regions billions of light-years apart have nearly identical temperatures. It's as if the universe somehow coordinated itself, despite these distant areas never being in contact. This uniformity is unexpected because the early universe was not perfectly smooth. Tiny fluctuations in temperature and density existed from the start, seeded by quantum processes in the moments after the Big Bang. Over billions of years, these fluctuations grew under the influence of gravity, forming the galaxies, stars, and planets we see today. But these initial irregularities were so small that it's hard to explain how the universe became so evenly distributed on such a large scale. One of the leading theories to resolve the horizon problem is cosmic inflation, which was proposed in the 1980s by physicist Alan Guth. Inflation suggests that in the first fractions of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion. During this brief moment, the universe grew exponentially, expanding faster than the speed of light. While this might sound impossible, it's important to note that the speed of light limits how fast things can move through space, not how fast space itself can expand. Inflation provides a solution to the horizon problem because it allows regions that are now far apart to have once been much closer together. Before inflation began, these regions could have exchanged energy and information, smoothing out their temperatures and densities. Then, during inflation, these well-mixed regions were stretched across the universe, creating the uniformity we observe today. This rapid expansion also explains why the CMB looks the same in every direction, despite the seemingly vast distances involved. Inflation doesn't just address the horizon problem, it also accounts for other features of the universe. For example, it explains why the universe appears flat on large scales rather than curved. The rapid expansion of inflation would have stretched any initial curvature, much like how a small section of a sphere can look flat when viewed up close. This prediction matches observations, which show that the universe is flat to within a tiny margin of error. Another intriguing consequence of inflation is the generation of small fluctuations in the density of matter. During inflation, quantum effects would have created tiny variations in the energy field, driving the expansion. These variations were then stretched to cosmic scales, seeding the irregularities that would later grow into galaxies and clusters. This idea is supported by detailed measurements of the CMB, which reveal slight variations in temperature that match the predictions of inflationary theory. Despite its success in explaining the horizon problem and other puzzles, inflation is not without its challenges. One of the biggest questions is what caused inflation to start, and what brought it to an end. Scientists propose that a hypothetical energy field called the inflaton drove the rapid expansion. However, the exact nature of this field remains unknown, and finding direct evidence for it is a major goal of modern cosmology. There are also alternative theories to inflation, though none are as widely accepted. Some propose that the universe we observe is just one part of a larger multiverse, where different regions might have different physical laws. Others suggest that the universe underwent a series of cycles, alternating between periods of expansion and contraction, with each cycle erasing the irregularities of the one before. These ideas are intriguing but difficult to test, leaving inflation as the leading explanation for now. Without the uniformity established during inflation, the universe would look very different today. Galaxies might not have formed in the orderly patterns we see, and the conditions for life might never have arisen. Einstein rings, cosmic magnifying glasses in action. Einstein rings are these glowing circular arcs of light that appear when a massive object, like a galaxy or a cluster of galaxies, bends the light from a more distant object directly behind it. Named after Albert Einstein, who predicted the effect in his theory of general relativity, Einstein rings are rare and serve as natural magnifying glasses, allowing astronomers to study objects that would otherwise be too faint or too far away to observe. The formation of an Einstein ring begins with a process called gravitational lensing. Light usually travels in straight lines, but when it passes near a massive object, the object's gravity bends the path of the light, much like how a glass lens bends light to form an image. This bending occurs because massive objects warp the fabric of space-time, curving the path that light follows. If the alignment between the distant object, the massive lensing object, and the observer is just right, the light from the distant source forms a complete ring around the lens. This perfect alignment is what creates the striking and symmetrical Einstein ring. Most Einstein rings aren't perfect circles, though. Slight misalignments or uneven distributions of mass in the lensing object can distort the ring into arcs or partial rings. These variations are just as valuable to scientists as perfect rings because they reveal details about the lensing object's structure. By analyzing the distortions, astronomers can map the mass of the lensing galaxy or cluster, including the dark matter that makes up most of its mass. Dark matter doesn't emit light, but its gravitational effects are clearly visible in how it bends light and shapes Einstein rings. Einstein rings are powerful tools for studying distant galaxies. The magnification caused by gravitational lensing can make faint, faraway objects appear much brighter and larger than they would otherwise. This magnification allows astronomers to observe galaxies that formed billions of years ago, during the early stages of the universe. By studying the light from these galaxies, scientists can learn about how stars and galaxies formed and evolved over cosmic time. The rings also help measure the distances to galaxies and determine their redshifts. Redshift occurs because the universe is expanding, stretching the wavelengths of light from distant objects. The more distant a galaxy is, the greater its redshift. Einstein rings provide highly magnified views of these galaxies, making it easier to analyze their light and understand their properties. One of the most famous examples of an Einstein ring is known as the Einstein Cross. Located in the constellation Pegasus, the Einstein Cross consists of 4 images of the same distant quasar, arranged in a cross-like pattern around a foreground galaxy. The light from the quasar has been bent and split by the gravity of the intervening galaxy, creating multiple images of the same source. Complete Einstein rings are rarer, but they have been captured in stunning detail by telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array, or ALMA. These telescopes can observe light across a range of wavelengths, from visible to radio, revealing the full extent of the lensing effect. One of the most striking Einstein rings ever observed is the molten ring, a bright, nearly perfect circle of light around a massive galaxy. This ring is the magnified light of a galaxy over 11 billion light-years away, allowing scientists to peer into a time when the universe was just a fraction of its current age. Gravitational lensing, and Einstein rings in particular, have also been used to measure the Hubble constant, a key value that describes the rate of the universe's expansion. By observing how the light from a background galaxy or quasar is delayed as it travels along different paths around the lensing object, scientists can calculate the distance to the lens and the background source. These time delays, combined with redshift measurements, provide an independent way to estimate the Hubble constant. This method has become increasingly important in recent years, as different techniques for measuring the Hubble constant have yielded slightly different results, leading to what's known as the Hubble tension. Finding Einstein rings requires a combination of luck and precise observation. The alignment of the source, lens, and observer must be almost perfect, which is rare in the vastness of the universe. But advancements in telescope technology and survey techniques have made it easier to identify potential gravitational lenses. Automated algorithms can now sift through massive amounts of data to find lensing candidates, leading to the discovery of more Einstein rings than ever before. Gravitational lensing by dark matter, invisible architects of the universe. Gravitational lensing offers a rare glimpse into the hidden side of the universe. Among its most impactful applications is the study of dark matter, which makes up about 85% of the universe's total matter. Unlike normal matter, dark matter does not emit, absorb, or reflect light. It is invisible to telescopes and undetectable through conventional means. Yet its presence is undeniable, revealed by its gravitational pull and the way it bends light from distant objects. Through gravitational lensing, scientists have found a way to map this unseen matter. The amount and pattern of the bending of light by gravitational lensing depends on the mass of the lensing object, including both visible matter and dark matter. By analyzing these distortions, scientists can calculate the distribution of mass in the lensing object, effectively creating a map of the dark matter within it. One of the first major clues to the existence of dark matter came from studies of galaxy clusters. In the 1930s, Astronomer Fritz Zwicky observed that galaxies within the Coma cluster were moving much faster than expected based on the visible matter in the cluster. He concluded that there must be additional, unseen mass providing the necessary gravitational pull to hold the cluster together. Decades later, gravitational lensing confirmed this finding. The distortions in light from background galaxies passing through clusters revealed far more mass than was visible in stars, gas, or dust. Gravitational lensing provides a unique way to measure dark matter because it doesn't rely on the matter interacting with light or other particles. Instead, it measures the gravitational effects directly, making it one of the most reliable methods to study dark matter. By comparing the distribution of visible matter, such as stars and gas, with the overall mass distribution inferred from lensing, scientists can determine how much of a galaxy or cluster is made up of dark matter. These studies have shown that dark matter is not evenly distributed. Instead, it forms clumps and halos around galaxies and clusters, extending far beyond the visible edges of these structures. In individual galaxies, dark matter halos provide the gravitational pull needed to explain the rotation speeds of stars at their outer edges, which would otherwise be too fast based on visible mass alone. In galaxy clusters, dark matter halos bind hundreds or even thousands of galaxies together, creating some of the largest structures in the universe. Strong gravitational lensing, where light is bent so much that it forms arcs or multiple images, is the most dramatic example of this phenomenon. These cases allow scientists to study the detailed structure of dark matter in the lensing object. For example, by examining how the images of background galaxies are distorted, researchers can map the clumps of dark matter within a galaxy cluster. This reveals not just the overall mass of the cluster, but also the small-scale distribution of dark matter within it. Weak gravitational lensing is also a useful tool for studying dark matter. Unlike strong lensing, weak lensing involves subtle distortions in the shapes of background galaxies, which can only be detected statistically by observing many galaxies at once. These distortions are caused by the combined gravitational effects of dark matter across vast regions of the universe. By analyzing weak lensing, scientists can create large-scale maps of dark matter, showing how it is distributed across the cosmos. These maps have revealed that dark matter forms a web-like structure, with filaments connecting dense clusters of galaxies and vast empty regions known as voids. The study of gravitational lensing by dark matter has led to some surprising discoveries. One of the most striking examples is the Bullet Cluster, a pair of galaxy clusters that collided about 1.5 billion years ago. Observations of the Bullet Cluster using X-rays showed that the hot gas, which makes up most of the visible mass in the clusters, was slowed down by the collision and displaced from the galaxies. However, gravitational lensing revealed that most of the mass associated with dark matter passed through the collision almost unaffected. This separation of dark matter and visible matter provides strong evidence for the existence of dark matter and shows that it interacts weakly, if at all, with normal matter and itself. Gravitational lensing has also been used to test theories that seek to explain dark matter as a modification of gravity rather than a new form of matter. These theories, known as modified Newtonian dynamics, aka MOND, or other modified gravity models, proposed that the observed effects attributed to dark matter could instead be explained by changing the laws of gravity at large scales. However, the patterns of lensing observed in galaxy clusters and large-scale structures are consistent with the presence of dark matter, making it difficult for modified gravity theories to fully account for the data. Dark matter may consist of unknown particles, such as weakly interacting massive particles, called WIMPs or axions, that have yet to be directly detected. By studying the distribution and behavior of dark matter through lensing, scientists hope to learn more about its properties, such as whether it is cold, meaning that it moves slowly, or warm, meaning that it moves more quickly. These properties affect how dark matter clumps together and influences the formation of galaxies and clusters. Observations of lensed quasars have revealed anomalies in the light patterns, suggesting the presence of small clumps of dark matter within the lensing galaxies. These clumps, known as subhalos, are too small to contain stars or other visible matter, but are predicted by simulations of cold, dark matter. Detecting these subhalos provides further evidence for the nature of dark matter and helps refine models of how it behaves. Upcoming surveys, such as those from the Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, and the European Space Agency's Euclid mission, will provide unprecedented data on weak lensing, mapping dark matter across billions of light years. These surveys will further refine our understanding of dark matter's role in the universe. The Lyman Alpha Forest, the light traces of the early universe. The Lyman Alpha Forest is a faint yet invaluable imprint of the early universe, a cosmic record etched into the light from distant quasars. This pattern, consisting of countless absorption lines, is formed as the quasar light travels through vast stretches of intergalactic space, interacting with clouds of hydrogen gas along the way. Each dip in the light spectrum marks a place where hydrogen has absorbed photons of a specific wavelength, leaving behind a detailed map of the matter that filled the universe billions of years ago. The process begins with a quasar, an intensely bright source of light powered by a supermassive black hole at the center of a galaxy. These quasars emit light across a wide range of wavelengths, including ultraviolet. As the light travels toward Earth, it passes through countless regions of intergalactic gas, much of which is composed of neutral hydrogen. Neutral hydrogen absorbs light at a precise wavelength known as the Lyman alpha line, which corresponds to the energy required to excite the hydrogen atom's electron to a higher energy level. The absorption creates dark lines in the quasar's spectrum, each corresponding to a specific patch of gas along the line of sight. The universe is expanding, and as it does, light traveling through space is stretched to longer, redder wavelengths. This redshift shifts the Lyman alpha absorption lines to different parts of the spectrum, depending on how far the light has traveled. Each line in the Lyman alpha forest represents a different redshift, a marker of the distance and time the light has traversed. By studying these lines, astronomers can effectively trace the distribution of hydrogen gas throughout the universe and across billions of years of cosmic history. Hydrogen gas is not evenly distributed, but instead forms the cosmic web, which consists of filaments of gas and dark matter that stretch across vast distances, connecting clusters of galaxies and enclosing immense empty regions known as voids. The Lyman alpha forest reveals this structure, with denser regions of gas creating stronger absorption lines and less dense areas leaving the quasar light mostly untouched. These absorption lines act as a kind of cosmic fingerprint, encoding information about the conditions of the early universe. For instance, the width and depth of the lines reveal the temperature and density of the gas they represent. In the early universe, the first stars and galaxies began to form within the denser regions of the cosmic web. Their radiation ionized the surrounding hydrogen, heating it and transforming it from a neutral state to a charged plasma. This process, known as reionization, left a distinct mark on the Lyman alpha forest, helping astronomers pinpoint when and how it occurred. By mapping the gas traced by the Lyman alpha forest, scientists can infer the underlying distribution of dark matter. This mapping reveals how dark matter clumped together over time, creating the scaffolding for galaxies and galaxy clusters to form. Quasars themselves play a critical role in this research. Their intense brightness allows their light to pierce through the otherwise faint hydrogen gas of the intergalactic medium. However, quasars are relatively rare, and only a small fraction of them are bright enough to produce a detailed Lyman alpha forest. As telescopes have grown more powerful, the number of observable quasars has increased dramatically, allowing scientists to study the Lyman alpha forest across larger portions of the sky. The Sloan Digital Sky Survey, or SDSS, has been a groundbreaking project in this regard, providing a treasure trove of quasar spectra. With this data, astronomers have constructed detailed maps of the Lyman Alpha Forest, spanning billions of light years. These maps have helped refine models of how the universe evolved after the Big Bang. By analyzing the distribution of absorption lines at different redshifts, scientists can measure how the universe's expansion rate has changed over time. This, in turn, provides clues about the nature of dark energy and how it affects the growth of cosmic structures. The gas traced by the forest represents a time when the universe was only a fraction of its current age, just a few 100 million years after the Big Bang. Yet, this gas is the same material that later condensed to form galaxies, stars, and eventually the planets and life we see today. By studying the Lyman Alpha Forest, astronomers are effectively looking at the raw ingredients of the cosmos and tracing their transformation over billions of years. The Great Attractor, a cosmic mystery, pulling galaxies together. The Great Attractor is a mysterious gravitational anomaly so powerful that it pulls entire galaxy clusters toward it, including our own Milky Way. This unseen force lies hidden behind dense regions of stars and gas, making it one of the most intriguing puzzles in modern astronomy. Scientists have spent decades trying to uncover its secrets, piecing together clues about what it might be and how it shapes the motion of galaxies across immense distances. The discovery of the Great Attractor began in the 1970s and 1980s, when astronomers noticed something strange about the motion of galaxies in our local region of the universe. Instead of moving away from each other uniformly, as expected in the expanding universe, many galaxies, including the Milky Way, were found to be heading toward a particular region of the sky. This movement couldn't be explained by the known distribution of matter, leading scientists to suspect the presence of a massive, unseen structure exerting a gravitational pull. This peculiar motion, known as the peculiar velocity, suggested that the Milky Way and thousands of other galaxies were being drawn toward a vast region located about 150 to 250 million light-years away in the direction of the constellations Norma and Triangulum Australe. This mysterious pull was named the Great Attractor, a term that captures both the enormity of its influence and the lack of clarity about what it truly is. Its location lies in what astronomers call the zone of avoidance, a part of the sky obscured by the dense plane of the Milky Way. The light from distant objects in this region is blocked by clouds of gas and dust, making it difficult to observe using traditional telescopes. Despite these obstacles, astronomers have developed methods to peer through the zone of avoidance, including using radio waves and X-rays, which can penetrate the intervening material. Observations have revealed a complex region dominated by massive galaxy clusters such as the Norma cluster. These clusters are filled with galaxies, hot gas, and dark matter, all contributing to the gravitational pull felt across such vast distances. However, the mass of these visible structures alone cannot fully account for the motion of galaxies toward the Great Attractor. This discrepancy suggests that there may be even more massive structures lurking beyond the reach of current observations, hidden behind the dense material of our galaxy or at even greater distances. One possibility is that it represents a massive supercluster of galaxies, far larger than any known local structure. Superclusters are the largest gravitationally bound systems in the universe, and their immense mass can influence the motion of galaxies over hundreds of millions of light years. The Great Attractor might be part of an even larger system, a concentration of matter that helps define the cosmic web. Another clue about the Great Attractor comes from its connection to the Shapley supercluster, an enormous concentration of galaxies located roughly 650 million light-years away. Some scientists believe the Great Attractor might be a waypoint in a larger gravitational flow toward the Shapley supercluster. In this view, the Great Attractor's influence is part of a chain of structures guiding the motion of galaxies, with even more massive regions farther out, exerting a pull. The concentration of dark matter in and around the Great Attractor could explain its ability to pull galaxies across such vast distances. Despite decades of research, the exact nature and composition of the Great Attractor remain elusive. One reason for this uncertainty is the difficulty of accurately measuring galaxy motions. The peculiar velocities caused by the Great Attractor are relatively small compared to the overall expansion of the universe, making them challenging to separate from other effects. Additionally, the obscured region where the Great Attractor resides limits the data available for analysis. Observatories like the Parkes Radio Telescope in Australia and the Chandra X-ray Observatory have helped in mapping the distribution of galaxies and galaxy clusters in the zone of avoidance, uncovering structures that may contribute to the Great Attractor's pull. Preons, theoretical building blocks of subatomic particles. Preons are theoretical particles that might serve as the building blocks of quarks and leptons, the fundamental particles that make up everything we see around us. While the standard model of particle physics, our current framework for understanding subatomic particles, describes quarks and leptons as indivisible, preons challenge that view by suggesting there's an even deeper level of structure. The standard model is one of the most successful theories in science, explaining the behavior of matter and forces with extraordinary precision. It describes particles like electrons and neutrinos, which are types of leptons, as well as quarks, the particles that combine to form protons and neutrons. But despite its successes, the standard model has gaps. It doesn't explain certain phenomena, like the nature of dark matter, or why the universe contains more matter than antimatter. For some scientists, this suggests the standard model might not be the final answer. Preons are one idea that could take us closer to understanding the universe at an even more fundamental level. The concept of preons was first introduced in the 1970s as part of an effort to simplify the complex zoo of particles predicted and observed by the standard model. If quarks and leptons were made of even smaller components, the number of fundamental particles could be drastically reduced. Instead of treating electrons, neutrinos, and all 6 types of quarks as fundamental, preons propose that these particles are combinations of just a few basic building blocks. This idea is similar to how our understanding of the atom evolved. At one time, atoms were thought to be indivisible. Then came the discovery of the nucleus, protons and electrons, followed by the realization that protons and neutrons were made of quarks. Preons extend this pattern, suggesting that quarks and leptons are not fundamental, but are instead made of smaller components. Theoretical models of preons vary, but they generally propose that preons combine in different ways to form the particles we observe. For example, a proton, made of 2 up quarks and 1 down quark, could ultimately be a combination of preons arranged in a specific structure. Similarly, an electron, a lepton, might also be made of preons, but in a different configuration. By unifying the building blocks of quarks and leptons, preon theories aim to reduce the complexity of particle physics into something more elegant and unified. One of the challenges in developing preon theories is ensuring they align with experimental evidence. The standard model has been tested extensively, and any theory involving preons must reproduce its predictions. Preon models also need to account for the masses of quarks and leptons, their interactions, and their unique properties, such as electric charge. This is a tall order because preon theories often introduce new particles or forces, which could have detectable effects in particle accelerators like the Large Hadron Collider. Despite these challenges, preons remain an intriguing idea because they might address some of the unanswered questions in physics. For instance, preons could offer insights into why there are 3 generations of particles in the standard model, each with increasing mass but identical charge and interactions. This pattern, often called the flavor puzzle, is unexplained in the standard model, but might be a natural outcome of preon configurations. Preons could also shed light on the masses of particles. The masses of quarks and leptons vary widely, and the standard model does not explain why. If these particles are made of preons, Their masses might depend on how preons interact or are arranged. The Standard Model describes 3 of the 4 fundamental forces: electromagnetism, the weak nuclear force, and the strong nuclear force. It doesn't include gravity or explain how these forces might emerge from a single underlying principle. Some preon models suggest that the interactions between preons could give rise to these forces in a unified way, potentially linking them to gravity and bringing us closer to a theory of everything. Experimental evidence for preons has been elusive. If preons exist, they would need to be incredibly small, much smaller than quarks or leptons, and their effects might only become apparent at energy scales far beyond what current particle accelerators can achieve. Some scientists have searched for signs of preons by looking for deviations from the predictions of the Standard Model. For example, high-energy collisions in particle accelerators might reveal unexpected patterns in how particles scatter or decay, which could hint at an underlying structure. One possible hint of preons comes from the idea of compositeness. If quarks and leptons are composite particles made of preons, they might exhibit subtle signs of internal structure, such as slight deviations from point-like behavior. Experiments at facilities like the Large Hadron Collider are sensitive to such effects, but so far, no definitive evidence of compositeness has been found. The lack of direct evidence doesn't rule out preons, but it does place constraints on their properties. For example, if preons exist, they must be tightly bound within quarks and leptons, with binding energies so high that they can't be separated under normal conditions. This would make preons effectively invisible in experiments designed to probe particle interactions. Preons also face competition from other theories aiming to extend the Standard Model. String theory, for instance, suggests that all particles are vibrations of tiny strings rather than made of smaller components. Other theories propose entirely new particles or symmetries to explain the gaps in our understanding. Preons are just one piece of this larger puzzle, and their ultimate role, if any, in the universe's structure remains uncertain. Neutrinos, the universe's most elusive particles. Neutrinos are incredibly tiny, almost massless particles that interact so weakly with other matter that trillions of them pass through you every second without leaving a trace. These ghost-like particles are essential for understanding the universe, yet they are also among the most difficult to study. Neutrinos were first theorized in the early 20th century as a way to solve a problem in physics. When scientists observed certain nuclear reactions, like beta decay, they noticed that energy seemed to disappear. This violated the principle of conservation of energy, a fundamental rule in physics. In 1930, the physicist Wolfgang Pauli proposed that an invisible particle was carrying away the missing energy. This particle, later named the neutrino by Enrico Fermi, was incredibly small and had no electric charge, making it nearly impossible to detect. The first direct detection of neutrinos didn't happen until 1956, more than 2 decades after they were proposed. Scientists used a large tank of liquid to capture a small number of neutrinos produced by a nearby nuclear reactor. Even then, the interactions were so rare that detecting just a handful of neutrinos took months of observation. This marked the beginning of neutrino astronomy, a field dedicated to studying these elusive particles. Neutrinos come from many sources. Some are produced in the Sun, where nuclear fusion powers its immense energy output. In the Sun's core, hydrogen nuclei combine to form helium, releasing neutrinos as byproducts. These solar neutrinos flood space and reach Earth in vast numbers. By studying them, scientists have learned a great deal about how the Sun works and confirmed key aspects of nuclear physics. Supernovae are another major source of neutrinos. When a massive star reaches the end of its life, it can explode in a supernova, releasing an enormous amount of energy. Most of this energy, around 99%, is carried away by neutrinos. These neutrinos provide a direct look at the violent processes occurring in a collapsing star's core, offering clues about the creation of heavy elements and the formation of neutron stars or black holes. In 1987, neutrinos from a supernova in a nearby galaxy were detected on Earth, marking one of the most significant events in neutrino research. The detection occurred before the supernova's light reached telescopes, highlighting the unique role neutrinos play in providing early warnings of cosmic events. This observation also confirmed theories about supernovae and demonstrated the potential of neutrino detectors to study phenomena far beyond our solar system. Neutrinos are produced not only by cosmic events, but also by human activities. Nuclear reactors generate vast numbers of neutrinos during the fission process. These reactor neutrinos have been used to study neutrino oscillations, a phenomenon that reveals the particle's ability to change from one type to another as they travel. There are three known types of neutrinos, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The discovery that neutrinos can oscillate between these flavors was groundbreaking, proving that neutrinos have mass, even if it is incredibly small. The weak interaction of neutrinos with matter makes them challenging to study, but it also gives them unique advantages. Unlike light or charged particles, neutrinos can pass through dense regions of space without being absorbed or scattered. This makes them perfect messengers from distant and extreme environments, such as the cores of stars, supernovae, or the regions near black holes. By detecting and studying neutrinos, scientists can probe areas of the universe that are otherwise hidden. Neutrino detectors are extraordinary pieces of equipment, often located deep underground to shield them from cosmic rays and other background noise. One famous example is the Ice Cube Neutrino Observatory in Antarctica, which uses a cubic kilometer of clear ice to detect neutrinos. When a neutrino interacts with the ice, it produces a faint burst of light that can be captured by sensitive instruments. Despite its immense size, Ice Cube only detects a few neutrinos each day because of the particle's rarity and weak interactions. Another prominent detector is Super Kamiokande in Japan, a massive tank filled with ultra-pure water. Photomultiplier tubes line the tank, capturing the tiny flashes of light created when neutrinos collide with water molecules. These detectors are marvels of engineering, designed to capture fleeting signals from particles that barely interact with the world around them. Neutrinos interact only through the weak nuclear force, making them valuable for studying this elusive force in detail. Their behavior has already challenged the standard model, particularly through the discovery of neutrino oscillations, which the model couldn't initially explain. Beyond particle physics, neutrinos have the potential to reveal the history and structure of the universe itself. Some theories suggest that neutrinos played a role in shaping the early universe, influencing the distribution of matter and the formation of galaxies. Neutrinos from the Big Bang, called relic neutrinos, still exist today, though they are extremely difficult to detect because they have cooled and slowed over billions of years. If scientists can find a way to study these relic neutrinos, it could provide data from the universe's earliest moments. One of the biggest mysteries surrounding neutrinos is their exact mass. While it's known that they have mass, the precise value remains uncertain. Experiments are underway to measure it more accurately, as it could have profound implications for cosmology and particle physics. The mass of neutrinos affects the formation of large-scale structures in the universe, such as galaxies and galaxy clusters, making it a key parameter in understanding how the cosmos evolved. Neutrinos are also being studied for their potential role in answering questions about matter and antimatter. The universe is filled with matter, but scientists believe that equal amounts of matter and antimatter were created during the Big Bang. Something must have caused a slight imbalance, allowing matter to dominate. Neutrinos might hold the answer. Certain properties of neutrinos, such as whether they are their own antiparticles, could provide clues to this fundamental mystery. Axions, hypothetical keys to the dark matter puzzle. Axions are hypothetical particles that, if they exist, could hold the key to understanding dark matter. The story of axions begins not with dark matter, but with a problem in particle physics. The Standard Model explains many aspects of the subatomic world, including the behavior of particles and the forces they interact with. However, one part of the model, related to the strong nuclear force, raised a puzzling question. The strong force, which binds protons and neutrons together in atomic nuclei, should allow for certain kinds of symmetry breaking. Yet, experiments showed that these violations didn't happen. This led to what's called the strong CP problem, where CP refers to a combination of charge and parity symmetries. In the 1970s, theoretical physicists proposed a solution to this problem. They suggested that a new field permeates the universe, and this field would naturally cancel out the expected symmetry violations. This idea predicted the existence of a particle associated with the field, the axion. At first, axions were thought to be extremely small and interact very weakly with other matter. Over time, scientists realized that these very properties made axions a perfect candidate for dark matter. Axions' weak interactions would make them invisible, but their abundance could give them enough combined mass to explain dark matter. The predicted properties of axions make them unusual. They are expected to have an incredibly small mass, perhaps billions of times lighter than an electron. Despite this, axions could exist in enormous numbers, filling the universe like a subtle sea. They are also thought to interact very weakly with ordinary matter, making them hard to detect. One prediction is that axions might convert into photons in the presence of a strong magnetic field. This property is central to many experiments designed to search for them. Detecting axions is a significant challenge, but scientists have devised clever methods to try. One approach uses resonant cavities, metal containers designed to amplify specific frequencies of electromagnetic waves. If axions pass through such a cavity in the presence of a magnetic field, they could convert into photons. These photons would create a faint signal that researchers could measure. Experiments like ADEMEX, the Axion dark matter experiment, are searching for these signals with ever-increasing sensitivity. Another method involves looking at astrophysical phenomena. If axions exist, they could affect the behavior of stars and other cosmic objects. For example, axions might escape from the cores of stars, carrying energy away and altering the star's lifetimes or brightness. Some researchers are studying specific types of stars, like white dwarfs or neutron stars, to see if their behavior matches what axion theories predict. Observations of supernovae and the CMB could also provide indirect evidence for axions. Space-based observatories and collaborations between ground-based telescopes are looking for signs of axions in the universe. Axions might cause unusual patterns in the polarization of light from distant sources such as quasars or galaxies. By carefully analyzing this light, scientists hope to uncover the subtle fingerprints of axions. Axions are not the only proposed candidates for dark matter. Other ideas include particles like WIMPs and sterile neutrinos. Each candidate has its strengths and challenges, but axions stand out because they address two problems at once: the strong CP problem in particle physics and the nature of dark matter. This dual-purpose appeal has made them a focus of intense research. One exciting possibility is that axions might not just be dark matter, but could also play a role in other cosmic phenomena. Some theories suggest that axions could form clumps or waves in space, creating structures that influence the behavior of galaxies or even black holes. These ideas are speculative, but highlight how axions could reshape our understanding of the universe if they are discovered. Scientists are pushing the boundaries of technology and theory to explore a realm of physics that lies far beyond what we currently know. Every experiment, whether it finds axions or rules them out, brings us closer to answering fundamental questions about the universe. If axions are discovered, it would be a breakthrough with profound implications, not just for dark matter, but for the entire framework of physics. Tachyons, theoretical messengers from beyond the speed of light. Tachyons are one of the most fascinating and controversial ideas in theoretical physics. These hypothetical particles are imagined to travel faster than the speed of light, a concept that challenges our understanding of the universe and the very foundations of physics. First proposed in the 1960s, tachyons remain purely theoretical, with no experimental evidence to support their existence. Despite this, they have sparked intense debate and inspired countless studies into the nature of time, space, and causality. The idea of tachyons arises from Einstein's theory of relativity. According to relativity, the speed of light is the ultimate speed limit in the universe. No object with mass can reach or exceed this speed, because doing so would require infinite energy. However, the equations of relativity also allow for the possibility of particles that never travel slower than light. These hypothetical particles, if they exist, would always move faster than light and could never be slowed down to subluminal speeds. Physicists name them tachyons, from the Greek word tachys, meaning swift. The possibility of faster-than-light particles is deeply intriguing but comes with significant complications. One of the most important issues is causality, the principle that cause precedes effect. If tachyons exist, their faster-than-light speed could allow information to travel backward in time. This means an event could be influenced by something that hasn't yet occurred, creating paradoxes that defy our understanding of logic and time. For example, a message sent via tachyons might arrive before it was sent. This potential to disrupt causality is a major reason why many physicists are skeptical of tachyons. The universe, as we understand it, operates in a way that preserves cause and effect relationships. The introduction of tachyons would require a radical rethinking of these principles, and many believe it would create contradictions that make the particles impossible. However, some physicists argue that certain frameworks, like quantum mechanics, might allow for tachyons to exist without violating causality, though these ideas remain speculative. Tachyons would also behave in ways that are entirely alien to our everyday experience. For instance, as a tachyon loses energy, it would speed up rather than slow down like ordinary particles. Conversely, gaining energy would cause it to slow down, approaching the speed of light from above but never crossing below it. This counterintuitive behavior is a direct consequence of the mathematics describing tachyons and highlights how different they would be from the particles we know. If tachyons could carry information, they might enable instantaneous communication across vast distances, or even messages sent across time. Some speculative theories suggest that tachyons could play a role in understanding quantum entanglement, the phenomenon where particles remain connected regardless of distance. However, these ideas are purely theoretical, as no evidence of tachyon-based communication has ever been found. Tachyons have also captured the imagination of science fiction writers and futurists. In many stories, they are used as a way to enable faster-than-light travel or communication, breaking the constraints of relativity. While these tales often take creative liberties with the science, they reflect the deep human fascination with overcoming the limits of space and time. The tachyon has become a symbol of pushing the boundaries of what is possible. The search for tachyons has inspired a range of experimental efforts, though none have succeeded in finding them. Some experiments have looked for indirect signs of tachyons, such as anomalies in particle interactions, or deviations from expected behavior in cosmic rays. Others have focused on high-energy environments where exotic particles might be created, like particle accelerators. Despite these efforts, no evidence of tachyons has emerged, leaving their existence an open question. One of the challenges in searching for tachyons is their nature. Because they are faster than light, they would not interact with ordinary particles in the usual way. This makes them incredibly hard to detect, as they would pass through matter almost without a trace. Some researchers speculate that if tachyons exist, they might only interact through weak or indirect forces, requiring entirely new methods of observation to find them. In addition to their potential physical existence, tachyons have implications for theoretical physics. They appear in some versions of string theory. In these models, tachyons sometimes emerge as mathematical artifacts, suggesting instabilities in certain configurations of the theory. While this doesn't necessarily mean tachyons exist in reality, their appearance in theoretical models keeps them relevant in discussions about the fundamental nature of the universe. Their faster-than-light nature puts them beyond the reach of current technology and observation, making them a subject of speculation rather than empirical study. This raises philosophical questions about the role of science in addressing ideas that might never be testable. Can a particle that defies all known methods of detection still be considered part of science? Or does it belong to the realm of philosophy and imagination? The strong force, how it shapes stars and black holes. The strong force is one of the most essential forces in the universe, holding the very fabric of matter together. It operates at the subatomic level, binding quarks into protons and neutrons, which in turn form the nuclei of atoms. Without the strong force, atoms couldn't exist, and the universe as we know it would be an empty void. But the strong force isn't just important for the building blocks of matter. It also plays a central role in the most powerful processes in the cosmos, from the fusion reactions that power stars to the extreme conditions that might influence the formation of black holes. The strong force is part of the standard model of particle physics. It is carried by particles called gluons, which act as the glue holding quarks together. Without gluons, quarks would fly apart, and the atomic nuclei that form the foundation of matter wouldn't exist. The strong force is incredibly powerful, much stronger than gravity or electromagnetism, but it operates over an extremely short range. Its influence is confined to the scale of an atomic nucleus, which is why we don't feel its effects in everyday life. Stars are powered by nuclear fusion, a process that occurs in their cores under immense pressure and temperature. In fusion, hydrogen nuclei, essentially protons, are forced so close together that the strong force overcomes their natural electromagnetic repulsion. Once the strong force takes hold, the protons merge to form helium, releasing enormous amounts of energy in the process. This energy is what we see as the light and heat of the stars. And it is the reason stars shine for billions of years. The energy released by the strong force in fusion is also what makes stars factories for heavier elements. As stars evolve, they burn through their hydrogen and begin fusing heavier elements like helium, carbon, and oxygen. In the final stages of a star's life, especially in massive stars, the strong force enables the fusion of even heavier elements, up to iron. Beyond iron, fusion requires more energy than it releases, but the strong force has already created the raw materials needed for life and planets. When massive stars reach the end of their life cycles, the strong force plays a dramatic role in their deaths. As the star exhausts its fuel, gravity causes it to collapse inward. In the core of the star, protons and electrons are crushed together to form neutrons. The strong force resists this collapse, creating a neutron star, one of the densest objects in the universe. A single teaspoon of neutron star material would weigh billions of tons on Earth. If the star is massive enough, even the strong force cannot prevent total collapse, leading to the formation of a black hole. In the case of neutron stars, the strong force holds neutrons together under extreme conditions. Neutron stars are essentially giant atomic nuclei, and the strong force prevents their total disintegration. The intense gravity of these stars balances against the degeneracy pressure of neutrons, a quantum mechanical effect that resists further compression. However, this balance is delicate. If the mass of the neutron star exceeds a critical limit, even the strong force is overwhelmed and the star collapses into a singularity. Near supermassive black holes, matter is subjected to intense gravitational forces, and scientists are still studying how the strong force operates under such conditions. Some theories suggest that in the presence of extreme gravity, the boundaries between quarks and gluons might blur, creating a state of matter called a quark-gluon plasma. This exotic state existed briefly after the Big Bang and could provide clues about the earliest moments of the universe. Quark-gluon plasma is a focus of research in particle physics, with experiments in particle colliders like the LHC attempting to recreate it. By smashing heavy ions together at nearly the speed of light, scientists can briefly produce conditions similar to those in the early universe. These experiments help researchers understand how the strong force behaves at incredibly high energies and temperatures. While these studies are conducted on Earth, they have implications for understanding cosmic phenomena, including black holes and neutron stars. The fusion processes in stars, driven by the strong force, have created nearly all the elements found in nature. From the carbon in our bodies to the iron in our blood, these elements were forged in the hearts of stars or during supernova explosions. The distribution of these elements across galaxies influences the formation of new stars, planets, and eventually life. The strong force operates within atomic nuclei, yet its effects ripple out to shape the life cycles of stars and the structure of galaxies. Understanding the strong force helps scientists connect the dots between particle physics and cosmology, revealing how the fundamental forces of nature work together to create the universe we observe. The Sun's long-lost sibling, the hypothetical nemesis, star. The idea of the Sun having a long-lost sibling, a companion star known as Nemesis, has captured the imagination of scientists and the public alike. This hypothetical star was theorized to have once orbited the Sun at a great distance, far beyond the planets, in a region of space so remote that it has remained undetected. The Nemesis hypothesis suggests that this star, if it existed, could have played a dramatic role in the history of our solar system. The Nemesis hypothesis was first proposed in the 1980s to explain a peculiar pattern observed in Earth's fossil record. Some scientists noticed that mass extinctions seem to occur roughly every 26 million years, a regularity that hinted at an external trigger. The idea was that a distant companion star, following an elongated orbit around the Sun, might occasionally pass through or near the Oort cloud. This cloud, a vast reservoir of icy objects and comets at the edge of the solar system, could be disturbed by Nemesis's gravitational pull. The resulting cascade of comets sent hurtling toward the inner solar system might have increased the chances of catastrophic impacts on Earth, leading to mass extinctions. Nemesis was theorized to be a small, faint star, possibly a red or brown dwarf. These types of stars are far dimmer than the Sun and notoriously difficult to detect, especially at great distances. If Nemesis were a brown dwarf, it would emit very little light and could remain hidden among the dense star fields of the Milky Way. Alternatively, it might no longer exist, having drifted away from the Sun over billions of years. While the hypothesis was intriguing, it faced significant challenges. One issue was the lack of direct evidence for such a companion. Despite extensive searches using telescopes designed to detect faint objects, no star-matching Nemesis's description has been found. Surveys like the 2-micron All-Sky Survey, or 2MASS, and the Wide Field Infrared Survey Explorer, or WISE, have scanned the sky for brown dwarfs and other dim objects. But none have turned up within the range where Nemesis was predicted to exist. Another problem with the Nemesis hypothesis is the reliability of the extinction pattern it was meant to explain. As paleontologists have gathered more data, the supposed 26 million year cycle has become less clear. Some scientists argue that the pattern may simply be a coincidence or an artifact of incomplete data. Without a clear and consistent extinction cycle, the need for a companion star to explain it becomes less compelling. However, the absence of direct evidence for Nemesis has not entirely ruled it out. Our solar system is vast, and the outer regions beyond the planets are still poorly understood. The Oort cloud itself has never been observed directly, as its objects are too small and distant to be seen with current technology. If Nemesis exists, it might be located even farther out, in a region of space we have yet to explore in detail. The search for Nemesis has also led to broader investigations into the possibility of other unseen companions to the Sun. Some researchers have proposed the existence of Planet 9, a hypothetical giant planet far beyond Neptune that might explain certain gravitational anomalies in the outer solar system. While Planet 9 and Nemesis are distinct hypotheses, both highlight how little we know about the distant reaches of our own solar system. Even if Nemesis doesn't exist, the idea has prompted valuable scientific exploration. For example, studying the effects of gravitational interactions in the Oort cloud has provided insights into how comets are sent toward the inner solar system. These icy bodies, often considered relics from the solar system's formation, carry important clues about its early history. Understanding their dynamics can help scientists piece together how the solar system evolved and why it looks the way it does today. The concept of Nemesis has also inspired discussions about the Sun's early history. Stars often form in clusters, born from the same cloud of gas and dust. These stellar nurseries can produce hundreds or even thousands of stars, many of which are gravitationally bound to each other in the early stages of their lives. Over time, interactions with other stars and the gravitational pull of the Milky Way can scatter these siblings across the galaxy. It's possible that the Sun did have a companion star in its youth, but it may have been ejected from the solar system billions of years ago. Astronomers have identified many binary and multiple star systems in our galaxy, where two or more stars orbit a common center of mass. Such systems are more common than solitary stars like the Sun. If the Sun did have a companion, understanding why it became isolated could reveal important details about the dynamics of young star clusters and the processes that shape planetary systems. The Kuiper Cliff. Why does the solar system just end? The Kuiper Belt is a ring of icy bodies that lies just beyond the orbit of Neptune. It is home to dwarf planets like Pluto and countless smaller objects that formed in the early days of the solar system. This belt represents a transitional zone between the familiar planets and the distant mysterious Oort cloud. But there's a puzzling feature in this region that astronomers call the Kuiper Cliff. Beyond a certain distance, the number of objects in the Kuiper belt drops off suddenly and dramatically, as if the solar system simply ends. This abrupt decline raises questions about the history and structure of the solar system. The Kuiper belt begins at around 30 astronomical units from the Sun, just beyond Neptune. It extends outward for tens of astronomical units with countless small icy bodies scattered throughout. These objects, sometimes referred to as Kuiper belt objects, or KBOs, are thought to be remnants from the solar system's formation, leftover pieces of material that never coalesced into planets. The population of KBOs increases steadily as you move outward from Neptune, but at around 50 astronomical units, something strange happens. The number of detectable objects plummets, creating what looks like a sharp edge to the belt. This is the Kuiper Cliff. Astronomers have long wondered what could cause such an abrupt cutoff. One possibility is that the Kuiper Cliff represents a natural limit to planetary formation. In the outer solar system, the Sun's gravitational influence weakens with distance. Beyond a certain point, the small building blocks of planets, tiny bits of rock and ice, may have been too widely spaced to come together and form larger objects. The Kuiper Cliff might simply mark the boundary where the conditions for planetary growth no longer existed. Another explanation involves the migration of the giant planets. In the early solar system, the orbits of Jupiter, Saturn, Uranus and Neptune were not as stable as they are today. These planets are thought to have migrated over time, moving outward from their original positions. This migration could have disrupted the Kuiper belt, scattering objects and altering its structure. The Kuiper Cliff might be a relic of this chaotic period, a region where the gravitational influence of the migrating planets stripped away material or prevented it from forming in the first place. But some scientists believe the Kuiper Cliff hints at something even more intriguing. The sudden drop-off in KBOs could be caused by the gravitational influence of an unseen object, perhaps a massive planet or even a small star. If such an object exists, it would lie far beyond the Kuiper belt, tugging on the outer reaches of the solar system and shaping the distribution of material. This idea has led to speculation about the existence of a hypothetical Planet 9, a massive planet that might orbit the Sun at an immense distance. The idea of Planet 9 emerged from studies of other distant objects in the solar system, particularly those in the scattered disk, a region beyond the Kuiper belt where icy bodies follow highly elliptical and tilted orbits. Some of these objects appear to be clustered in ways that suggest the presence of a large, unseen gravitational force. Planet 9, if it exists, could be responsible for these patterns. It might also explain the Kuiper cliff, creating a gravitational barrier that prevents objects from accumulating beyond a certain distance. The search for Planet 9 is ongoing, with astronomers using powerful telescopes to scan the skies for any sign of this elusive world. Its great distance makes it extremely difficult to detect, as it would reflect very little sunlight and move slowly across the sky. Another possibility is that the Kuiper cliff is not a feature of the Kuiper belt itself, but rather a limitation of our observations. Detecting distant objects in the outer solar system is incredibly challenging. KBOs are small, dark, and faint, making them difficult to spot even with advanced telescopes. It's possible that objects beyond the Kuiper cliff exist, but are simply too small or too far away for us to detect. As observational technology improves, astronomers may find that the apparent edge of the Kuiper belt is not as abrupt as it seems. Studying the Kuiper cliff and the Kuiper belt as a whole provides valuable insights into the early solar system. These regions contain some of the most pristine material left over from the Sun's formation, offering a window into the processes that shaped our planetary neighborhood. The composition and distribution of KBOs can reveal details about the conditions that prevailed in the solar nebula, the disk of gas and dust from which the Sun and planets formed. Similar belts of icy bodies are thought to exist around other stars, and these belts may play a key role in the dynamics of exoplanetary systems. By studying the Kuiper cliff and its possible causes, astronomers can gain a deeper understanding of how planets form and evolve, both in our solar system and across the galaxy. Planck stars, theoretical remnants at the heart of black holes. Black holes form when massive stars collapse under their own gravity, creating regions of space where gravity is so intense that nothing can escape. At the heart of a black hole, according to conventional theories, lies a singularity. This is a point where gravity becomes infinitely strong and the fabric of space-time is infinitely curved. But the concept of a singularity presents a significant problem for physics, as it defies the laws of nature as we understand them. To address this, some scientists have proposed a revolutionary idea that the center of a black hole might not contain a singularity, but instead a Planck star. A Planck star is a hypothetical object that exists at the very limits of physical understanding. It's named after the Planck scale, which represents the smallest measurable length, time, and energy scales in the universe. At this scale, quantum mechanics and gravity are expected to merge into a unified theory, a quantum theory of gravity. Planck stars are theorized to form when the extreme conditions inside a black hole prevent the complete collapse of matter into a singularity. Instead, quantum effects create an incredibly dense and compact object, stabilizing the black hole's core and avoiding the infinities associated with a singularity. The idea of Planck stars is rooted in loop quantum gravity, a theoretical framework that attempts to combine general relativity and quantum mechanics. Loop quantum gravity suggests that spacetime itself is not continuous, but is made up of discrete, tiny units, like a fabric woven from individual threads. Under this theory, the intense gravitational pressure inside a black hole cannot crush matter indefinitely. Instead, it reaches a limit determined by the quantum structure of spacetime. At this limit, matter could rebound, forming a Planck star rather than collapsing into a singularity. Black holes are known for their event horizons, the boundaries beyond which nothing can escape. According to classical physics, information about anything that falls into a black hole is lost forever. This creates a paradox because it conflicts with the principles of quantum mechanics, which state that information cannot be destroyed. If Planck stars exist at the cores of black holes, they might provide a way to preserve this information. The intense quantum effects at their surface could encode and eventually release the information, addressing the so-called information paradox. Planck stars might also change how we think about black hole lifetimes. According to Stephen Hawking's theory of black hole evaporation, black holes lose mass over time by emitting Hawking radiation, a process that eventually leads to their disappearance. But if Planck stars exist, the evaporation process might reveal their presence. As a black hole shrinks due to Hawking radiation, the event horizon would gradually approach the Planck star inside. Once the black hole has radiated most of its mass, the Planck star could emerge, releasing any remaining energy and information it contains. In the moments following the Big Bang, conditions were incredibly dense and hot, similar to the environment inside a black hole. Some scientists speculate that the early universe might have contained objects resembling Planck stars, and studying these theoretical remnants could provide clues about the universe's origin and evolution. By their nature, black holes are incredibly difficult to study directly. Their event horizons hide whatever lies within, and the extreme conditions at their cores make it impossible to observe Planck stars with current technology. But scientists are exploring indirect ways to test the idea. For instance, the patterns of radiation emitted during the final stages of black hole evaporation might carry signatures of Planck stars. Theoretical models of Planck stars also predict that they could produce unique gravitational wave patterns. Gravitational waves are ripples in space-time caused by massive objects moving or interacting. Collisions between black holes, for example, create gravitational waves that can be detected on Earth. If Planck stars exist, their presence inside black holes could alter the gravitational wave signals emitted during such events. Analyzing these signals might provide indirect evidence of their existence. In some theories, the quantum effects that prevent the formation of a singularity could create a kind of bounce effect, where matter that collapses into a black hole might eventually re-expand. Could a Planck star represent a bridge between a collapsing universe and an expanding one? If so, it might offer a new perspective on the cycles of cosmic evolution and the fate of the universe. If these objects exist, they could be a universal phenomenon, appearing in other extreme environments where matter is compressed to its limits. Studying Planck stars could reveal fundamental truths about the nature of matter, energy, and space-time, potentially leading to breakthroughs in our understanding of the cosmos. The photon sphere, where light orbits black holes. Around every black hole, there exists a region where gravity exerts such a powerful pull that even light cannot escape. While the event horizon often takes center stage in discussions about black holes, another fascinating and lesser-known feature is the photon sphere. This is the area where light does not escape or fall inward, but instead gets trapped in a delicate, endless orbit around the black hole. The photon sphere is a unique phenomenon, revealing the strange and counterintuitive effects of gravity near these mysterious objects. The photon sphere forms because black holes distort spacetime to an extreme degree. Normally, light travels in straight lines through space, but near a black hole, the curvature of spacetime forces light to bend. At a specific distance from the black hole, this bending is so precise that light rays can circle the black hole in a perfect orbit. This region, known as the photon sphere, is the last point where photons, particles of light, can maintain a stable path without spiraling into the black hole or escaping outward. For a non-rotating black hole, this distance is 1.5 times the radius of the event horizon. The photon sphere is not a solid surface or a single layer, but rather a region where orbits can occur. Unlike planets in our solar system that follow stable elliptical paths around the Sun, the orbits in the photon sphere are inherently unstable. A tiny nudge, even the slightest deviation in a photon's path, will send it either hurtling into the black hole or out into space. This instability is one reason why the photon sphere is so difficult to study directly. If you were observing a black hole from a distance, the photon sphere would contribute to the formation of the so-called black hole shadow. This shadow is not the actual size of the event horizon, but is magnified by the bending of light around the black hole. The photon sphere acts like a cosmic lens, bending light from distant stars and galaxies into a halo-like structure around the black hole. Observatories like the Event Horizon Telescope use this bending effect to capture images of black hole shadows, as seen in the groundbreaking 2019 image of the supermassive black hole at the center of the galaxy M87. The light that orbits in the photon sphere creates fascinating optical illusions. Imagine a photon emitted by a star behind the black hole. Instead of traveling in a straight line, the photon's path bends as it approaches the black hole, curving around it and potentially reaching an observer on the other side. If the photon orbits the black hole multiple times before escaping, the observer might see the same star in several positions simultaneously. The result is a warped, mirrored image of the universe, where objects appear distorted and duplicated in ways that defy intuition. For rotating black holes, or Kerr black holes, the situation becomes even more complex. The rotation of the black hole drags space-time along with it, a phenomenon known as frame dragging. This effect distorts the photon sphere, creating a region where light can orbit in one direction more easily than the other. The size and shape of the photon sphere depend on the black hole's spin. Studying the photon sphere provides insights into how matter and light interact with the extreme curvature of space-time. By analyzing the light patterns near the photon sphere, scientists can infer details about a black hole's mass, spin, and even the properties of the surrounding environment. For instance, the accretion disk, a structure of gas and dust spiraling into the black hole, emits radiation that can be bent and focused by the photon sphere, creating unique observational signatures. Because it is such an unstable and dynamic region, capturing and interpreting signals from this area requires highly precise instruments and advanced theoretical models. The faintness of the light and the extreme gravitational forces at play make observations incredibly difficult. Yet advancements in technology, such as interferometry and high-resolution imaging, are beginning to open up new possibilities. General relativity, Einstein's groundbreaking theory, predicts the existence and properties of the photon sphere with remarkable accuracy. However, alternative theories of gravity or modifications to general relativity could produce subtle differences in the photon sphere's behavior. Studying these differences could provide crucial clues about the fundamental nature of gravity and space-time. While a human could never survive the extreme forces near a black hole, imagining the view from the photon sphere reveals the surreal nature of curved space-time. If you were somehow positioned at the edge of the photon sphere, you would see light from all directions bent and twisted around you, creating a distorted panorama of the universe. Looking inward, you might see light that had orbited the black hole multiple times, giving you a glimpse into regions of space far away from your own. Quantum black holes, miniature giants of the universe. Traditional black holes are objects of immense size and mass, formed when massive stars collapse under their own gravity. Quantum black holes take this concept to the other side of the spectrum, existing as theoretical entities that could form at the smallest, subatomic levels of the universe. The idea of quantum black holes emerges from the realization that black holes are not bound by size. If a large enough mass is compressed into a sufficiently small space, it will form a black hole regardless of its scale. For most of the universe, the formation of black holes happens through astronomical events like the collapse of massive stars. But in the extreme conditions of the early universe, or within powerful particle collisions, even minuscule black holes might form. These are what we call quantum black holes. The concept of quantum black holes is deeply tied to theories of quantum gravity, particularly string theory. According to string theory, the universe has extra dimensions beyond the three we experience, and these dimensions could provide the conditions necessary for quantum black holes to form. If such black holes exist, they would be incredibly small, potentially on the order of the Planck length, which is about 10 to the power of minus 35 meters, a size so small that it defies comprehension. One of the reasons quantum black holes are so interesting is their potential to offer clues about the elusive connection between quantum mechanics and general relativity. These two pillars of modern physics describe very different aspects of reality. Quantum mechanics governs the behavior of particles at the smallest scales, while general relativity explains the force of gravity on massive objects. Quantum black holes would exist at the boundary where these two theories overlap, making them a natural laboratory for studying how gravity behaves in the quantum realm. Theoretical physicists have predicted several properties of quantum black holes. Unlike their larger counterparts, quantum black holes would not last long. They would radiate energy and lose mass through a process called Hawking radiation, named after the physicist Stephen Hawking, who first proposed it. Hawking radiation occurs when quantum effects near the event horizon allow particle-antiparticle pairs to form, with one particle escaping and the other falling into the black hole. For a quantum black hole, this process would happen incredibly quickly, causing it to evaporate almost as soon as it forms. Despite their fleeting nature, quantum black holes could shed light on the nature of spacetime at the smallest scales. In classical physics, spacetime is smooth and continuous, but quantum theories suggest it might be granular, like a fabric woven from tiny threads. The formation and evaporation of quantum black holes could reveal whether spacetime has this discrete structure and how it behaves under extreme conditions. Scientists are actively looking for evidence of their existence in particle accelerators like the LHC. These accelerators smash particles together at incredibly high energies, mimicking the conditions that might have existed in the early universe. If the energy levels are high enough and the extra dimensions predicted by string theory are real, it is possible that these collisions could produce quantum black holes. Detecting them would involve looking for specific patterns in the particles and radiation emitted during their evaporation. So far, no quantum black holes have been detected, but the search continues. Even their absence can tell us something important about the universe. If quantum black holes are not observed in high-energy experiments, it might suggest that the energy threshold for their formation is much higher than expected, or that extra dimensions do not exist. These findings would help refine or even challenge current theories, pushing our understanding of fundamental physics in new directions. Moments after the Big Bang, the universe was unimaginably hot and dense, with conditions that might have allowed quantum black holes to form spontaneously. If they did, they could have left behind subtle imprints on the universe that we might still observe today, such as tiny variations in the CMB radiation. These imprints could provide valuable clues about the universe's first moments and the laws that governed its rapid expansion. Another intriguing possibility is that quantum black holes could help solve the information paradox. In classical terms, when something falls into a black hole, all the information about its composition seems to be lost forever. However, quantum mechanics insists that information cannot be destroyed. This apparent contradiction is one of the biggest puzzles in modern physics. Quantum black holes, with their rapid formation and evaporation, might provide a way to study how information behaves in such extreme environments. Some theories suggest that the radiation emitted by a quantum black hole could carry encoded information about the matter it consumed, offering a potential resolution to the paradox. If they exist, they could provide a new perspective on the nature of reality itself. They might hint at the existence of a multiverse, where different universes with varying physical laws coexist. The properties of quantum black holes might vary depending on the specific conditions of each universe, offering a glimpse into a broader cosmic landscape. Zombie stars, white dwarfs that refuse to die. White dwarfs are often considered the last quiet stage of a star's life. These dense remnants form after a star exhausts its nuclear fuel, sheds its outer layers, and leaves behind a smoldering core. In this state, white dwarfs are incredibly stable. They slowly cool and fade over billions of years, no longer capable of sustaining nuclear fusion. However, some white dwarfs defy this tranquil ending, finding ways to reignite and come back to life in dramatic and violent ways. These are the so-called zombie stars, objects that refuse to stay dormant. One way white dwarfs reignite is through accretion. In binary star systems, a white dwarf can siphon material from a companion star. If the companion is a red giant or other massive star, its outer layers can expand and overflow onto the white dwarf. The material is mostly hydrogen and helium, and as it builds up on the white dwarf's surface, it becomes increasingly hot and dense. Eventually, conditions reach a critical point where nuclear fusion can begin again. But this fusion doesn't reignite the entire star. It happens in a runaway reaction on the surface, leading to a powerful explosion known as a nova. Novae are not rare in the universe. They can occur multiple times with the same white dwarf, as long as the companion star continues to donate material. These explosions eject material into space, temporarily brightening the star dramatically. But, despite their intensity, novae don't destroy the white dwarf itself. The star survives, waiting for another cycle of accretion to repeat the process. This cycle can make a white dwarf appear as if it's living multiple lives, reigniting again and again through material stolen from its companion. Not all white dwarfs settle for these temporary outbursts. Some take the process much further, accreting so much material that they reach a critical mass, known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. When this happens, the pressure and temperature at the white dwarf's core become extreme, triggering uncontrolled nuclear fusion. This leads to a catastrophic explosion called a Type Ia supernova. Unlike novae, Type Ia supernovae completely destroy the white dwarf, scattering its material into space and leaving no remnant behind. These explosions are so bright that they can outshine entire galaxies for weeks and are used by astronomers as cosmic yardsticks to measure distances across the universe. While Type Ia supernovae are well understood as the final fate of some white dwarfs, other scenarios involve white dwarfs that collide with each other. Such collisions occur in densely populated regions of space, like globular clusters or the crowded centers of galaxies. When two white dwarfs merge, their combined mass can exceed the Chandrasekhar limit, triggering a supernova. Alternatively, the collision might not result in an explosion, but instead form an even more massive white dwarf. In rare cases, this could reignite fusion in the core, giving the zombie star a new lease on life. These collisions and mergers are rare, but show that even stars presumed to be in their final stages can be dramatically altered by their environment. This unpredictability reveals the chaotic nature of the universe, where stellar life cycles can be rewritten by interactions with other stars or their surroundings. Some white dwarfs are part of a class of objects called recurrent novae. These systems repeatedly undergo nova outbursts, but with increasing intensity over time. Eventually, a recurrent nova system might cross the threshold to become a Type Ia supernova. Astronomers study these systems closely, as they provide clues about how mass transfer and accretion rates evolve over time. They also offer insight into the conditions that lead to some of the most powerful explosions in the cosmos. White dwarfs, through their novae and supernovae, play a crucial role in creating and spreading heavy elements like carbon, oxygen, and iron. When a white dwarf reignites or explodes, it sends these elements into space, enriching the interstellar medium. These materials later become the building blocks for new stars, planets, and even life itself. Without these processes, the universe would lack many of the elements essential for complex chemistry. Some theorists have proposed that certain white dwarfs might even reignite without external triggers like accretion or collision. These scenarios involve exotic physics, such as the gradual accumulation of dark matter particles in the star's core. If enough dark matter collects, it could lead to a destabilization of the star, triggering fusion or even a small-scale explosion. Because white dwarfs are so stable, they can exist for billions of years. When they reignite or explode, they provide information about their original stars, which may have formed when the universe was much younger. By studying these revived stars, astronomers can piece together the history of stellar evolution and the chemical enrichment of galaxies. Barred spiral galaxies, cosmic engines of star creation. Barred spiral galaxies are some of the most striking structures in the cosmos. Their defining feature is the bar, a long linear formation of stars, gas, and dust that stretches across the center of the galaxy and connects to its spiral arms. These galaxies are not just visually captivating, they are dynamic engines of star creation and evolution. The bar plays a critical role in shaping the galaxy's behavior, acting as a channel that directs material toward the galactic core, where it fuels intense star formation and other energetic processes. The bar forms as a result of gravitational interactions within the galaxy. In a spiral galaxy, the stars and gas in the disk move in intricate orbits influenced by the gravitational pull of the galaxy's mass. Over time, small instabilities in the distribution of mass can grow, creating the elongated structure of the bar. This process doesn't happen overnight. It takes millions of years for a bar to fully develop. Once it does, the bar becomes a stable and significant feature of the galaxy. Gas and dust in a galaxy are spread throughout its disk, but not all of it ends up in places where new stars can form. The bar acts as a mechanism to transport this material from the outer regions of the galaxy toward the core. As the gas flows inward along the bar, it encounters increasing density and pressure, which can trigger star formation. This inward flow also feeds the central supermassive black hole found in most galaxies, fueling phenomena like active galactic nuclei and quasars. The presence of a bar can lead to bursts of star formation near the galaxy's center. These starbursts can be extraordinarily productive, forming hundreds or even thousands of stars in a relatively short time. The newly formed stars are often massive and luminous, shining brightly and influencing their surroundings with powerful stellar winds and supernova explosions. These processes can further compress nearby gas, creating a chain reaction of star formation. In this way, the bar not only triggers star formation, but also helps to sustain it over extended periods. As bars channel material inward, they can gradually alter the distribution of stars and gas. Over time, the buildup of mass in the core can lead to the development of a more pronounced central bulge, a dense region of stars at the galaxy's center. This transformation can change the galaxy's classification, moving it from a pure spiral to a barred spiral, or even an elliptical-like appearance in extreme cases. The presence of a bar is therefore a key factor in a galaxy's evolutionary path. Not all barred spiral galaxies are the same. Some have strong, prominent bars that dominate their structure, while others have weaker, subtler bars. The strength and size of the bar depend on several factors, including the amount of gas in the galaxy, the distribution of mass, and the galaxy's interaction with nearby galaxies. Galactic collisions and mergers, for instance, can enhance or disrupt the formation of a bar. The bar's formation and stability depend in part on the galaxy's overall gravitational field, which is influenced by the presence of dark matter. Dark matter forms a halo around galaxies, providing the extra gravitational pull needed to hold them together. Understanding how dark matter interacts with the visible components of a galaxy can shed light on why some galaxies develop bars while others do not. Our own galaxy is a barred spiral. For a long time, astronomers debated whether the Milky Way had a bar, as our position within the galaxy makes it challenging to observe its overall structure. However, advances in telescopes and surveys, like the Spitzer Space Telescope, have provided clear evidence of the bar, which spans tens of thousands of light-years across the center of our galaxy. galactic bars are not permanent features. Over billions of years, a bar can weaken and dissolve, depending on the galaxy's dynamics. As the bar channels material inward, it can deplete the reservoir of gas available for star formation. Without this fuel, the processes that sustain the bar's structure may fade, leading to a more uniform and less dynamic appearance. Bars are more common in galaxies today than they were in the early universe, suggesting that they become more prevalent over time. This observation aligns with the idea that bars form as galaxies mature, reshaping themselves through internal and external interactions. By comparing barred and non-barred galaxies across different eras, researchers can piece together a more complete picture of how galaxies evolve. Hot Jupiters, gas giants. Defying orbital norms. Hot Jupiters are gas giants that defy the norms of planetary systems, orbiting their parent stars at incredibly close distances, often closer than Mercury is to the Sun. This proximity to their stars exposes these exoplanets to intense heat, leading to exotic atmospheric behaviors and posing questions about how such planets could have formed and migrated to their current positions. When astronomers first identified these planets, they were surprised. Gas giants in our own solar system, like Jupiter and Saturn, exist far from the Sun, where temperatures are low enough for gases like hydrogen and helium to condense during the formation process. This understanding led to the expectation that gas giants would typically form in the outer regions of a planetary system. Yet, the discovery of hot Jupiters showed planets as massive as or larger than Jupiter, orbiting at blistering speeds, completing a circuit around their stars in days or even hours. These planets' tight orbits mean they are subjected to immense stellar radiation. Surface temperatures on hot Jupiters can reach thousands of degrees, hot enough to vaporize many elements and molecules. Their atmospheres are inflated by the heat, causing them to expand to sizes much larger than Jupiter, despite having similar or even smaller masses. In some cases, the heat is so intense that these planets' atmospheres are slowly being stripped away by the stellar wind, creating tails of gas trailing behind them, much like comets. One of the greatest mysteries about hot Jupiters is how they ended up in such extreme orbits. The prevailing theory is that they formed much farther from their stars, in the colder outer regions of their planetary systems, where conditions were favorable for gas giant formation. After forming, they likely migrated inward through interactions with other planets, protoplanetary disk material, or even neighboring stars. These interactions could have nudged the planets into orbits that brought them closer to their stars, where gravitational forces locked them into their current tight paths. This process, known as orbital migration, is a key area of study in planetary science. The extreme environments of hot Jupiters make their atmospheres uniquely interesting. Observations have revealed atmospheric layers rich in exotic molecules and dynamic weather patterns. Some hot Jupiters have strong winds that whip across their surfaces at thousands of miles per hour, redistributing heat from the side facing the star to the cooler night side. In some cases, however, the heat distribution is uneven, leading to surprising thermal patterns. For example, one hemisphere might glow much hotter than the other, depending on how efficiently the atmosphere transports energy. Hot Jupiters also exhibit unusual atmospheric compositions. Spectroscopic studies using telescopes like the Hubble Space Telescope and the James Webb Space Telescope have detected water vapor, carbon monoxide, methane, and even exotic metals in their atmospheres. In some cases, heavier elements like iron and titanium have been found in gaseous states, raining down in molten form on the planet's surfaces. Despite their harsh conditions, hot Jupiters provide valuable insights into planetary systems and their formation. They are some of the easiest exoplanets to detect, primarily through two methods: the transit method and the radial velocity method. The transit method involves observing the slight dimming of a star as a planet passes in front of it, while the radial velocity method detects the gravitational tug of the planet on its star, causing the star to wobble slightly. Hot Jupiter's large sizes and close orbits make them especially prominent in both types of observations, allowing scientists to study them in great detail. The discovery of hot Jupiters in systems with no other large planets suggests that their inward migration may have disrupted their original planetary neighbors, scattering or ejecting them entirely. In other systems, smaller planets are found in orbits further out, indicating that hot Jupiters may have settled into stable configurations after their migrations. These differences highlight the varied evolutionary paths planetary systems can take. The gravitational pull of a massive planet so close to its star can induce tidal forces, heating the star's outer layers and altering its rotation. Over time, these interactions may even lead to the planet spiraling inward until it is eventually engulfed by the star. This process, though catastrophic for the planet, leaves behind signatures that astronomers can detect, offering a glimpse into the final stages of hot Jupiter lifespans. Their presence close to a star can destabilize the orbits of other planets, reducing the chances of finding Earth-like worlds in stable, habitable zones. However, some researchers speculate that moons orbiting hot Jupiters could harbor conditions suitable for life, provided they are shielded from the intense radiation by the planet's magnetic field or atmosphere. The diversity among hot Jupiters continues to surprise astronomers. Some have eccentric orbits, swinging close to their stars before retreating to cooler distances. Others are ultra-hot Jupiters, with temperatures so extreme that even molecules like water are torn apart into their atomic components. These variations suggest that the category of hot Jupiters may encompass a broad range of planetary types, each with its own unique story. Rogue exomoons. Could they harbor life? Rogue exomoons are thought to be moons that, for one reason or another, have broken away from their parent planets and are now drifting through the void of space. These lonely wanderers are similar in concept to rogue planets, which travel untethered to any star. However, as moons, they carry with them the complexities of being former satellites, potentially giving them unique characteristics. Exomoons, by definition, are moons that orbit planets outside our solar system. Most of these moons, if they exist in other star systems as they do here, likely remain bound to their planets. Yet, in the chaotic environments of forming planetary systems or during close encounters with other celestial bodies, a moon could be ejected from its orbit. The gravitational dance of large objects, particularly in young and crowded star systems, often leads to dramatic events. A planet might have a near collision with another massive body, pulling its moon away in the process. Alternatively, an exomoon might be slingshotted out during interactions between planets or clusters of planets in a system. Once freed, a rogue exomoon would no longer rely on the gravitational warmth or proximity to its host planet. Instead, it would face the cold and isolation of interstellar space. Without a nearby star to provide light and heat, these moons would appear as frozen, desolate worlds, much like the icy moons in our solar system that orbit distant planets such as Jupiter and Saturn. However, appearances can be deceiving. Scientists now recognize that habitability does not always require proximity to a star. A rogue exomoon might still generate heat internally through tidal forces or radioactive decay, creating pockets of warmth beneath its surface. One of the most compelling examples to consider is Europa, a moon of Jupiter. Europa has a thick ice shell, but is believed to host a liquid ocean beneath it, kept warm by tidal heating from its interaction with Jupiter's gravity. If a moon like Europa were ejected from its planetary system, it might retain enough internal heat to maintain liquid water for millions or even billions of years, depending on the size of the moon and its initial heat reserves. Life, if it had already taken hold in such an ocean, could theoretically survive under these conditions, shielded from the harshness of space by the ice above. Even without direct sunlight, such oceans could support ecosystems driven by chemical energy rather than photosynthesis. On Earth, life thrives in deep-sea hydrothermal vents, where heat and minerals from the planet's interior provide everything organisms need to survive. A similar process could occur on a rogue exomoon, with hydrothermal activity sustaining microbial or even more complex life. Detecting rogue exomoons is a significant challenge. Unlike rogue planets, which can sometimes be spotted through their gravitational effects or faint thermal emissions, moons are smaller and emit less heat. If they still carry remnants of their former planetary systems, such as debris or a faint atmosphere, these features might provide clues to their existence. Advances in telescope technology, such as next-generation infrared and radio observatories, could make detecting rogue exomoons more feasible in the future. If a rogue exomoon was once orbiting a gas giant, it might retain characteristics of its former environment, such as volatile-rich atmospheres or magnetic interactions. However, if it originated around a rocky planet, it could carry traces of geological activity or even the building blocks of life. Understanding these origins would require detailed analysis, possibly through spectroscopy. Another factor to consider is the possibility of rogue exomoons traveling in clusters. When a moon is ejected, it might not leave alone. Other moons from the same system, or even parts of the planet it once orbited, could be pulled away in a gravitational upheaval. These traveling companions could create miniature systems of their own, with smaller bodies orbiting a central rogue moon or planet. This scenario might offer additional stability or complexity to any ecosystems that could exist there. While rogue planets are typically larger and may retain atmospheres thick enough to trap heat, rogue exomoons are smaller and less likely to have substantial atmospheres. This smaller size and mass make them more vulnerable to the cold of space. Additionally, rogue planets often form independently or are ejected from star systems, whereas rogue exomoons have a clear history of being satellites, which may influence their composition and structure. If a rogue exomoon was ejected early in its system's history, it might carry traces of the chemical or biological processes that were taking place at that time. These remnants could provide invaluable information about the conditions that existed in different parts of the galaxy billions of years ago. In this way, studying rogue exomoons could reveal not only their own secrets, but also the histories of the star systems they once called home. The mystery of Planet 9, a ghostly giant, somewhere far beyond Neptune, in the icy and dark outer reaches of the solar system, there might be a massive planet quietly orbiting the Sun. It has never been seen, but its existence is inferred from the strange behavior of distant objects in the Kuiper Belt, a region of icy bodies beyond Neptune. These trans-Neptunian objects, or TNOs, exhibit orbits that suggest they are under the influence of something powerful and unseen. That something might be a planet, huge, distant, and elusive. The concept of a hidden planet isn't new. For centuries, astronomers have speculated about undiscovered members of the solar system. Uranus, for example, was discovered in 1781, and irregularities in its orbit eventually led to the discovery of Neptune in 1846. Pluto, originally thought to be a planet, was found in 1930, though it was far smaller than expected and later reclassified as a dwarf planet. Planet 9, if it exists, would be much larger, perhaps 10 times the mass of Earth, and located at a staggering distance, hundreds of times farther from the Sun than Earth. Evidence for Planet 9 comes primarily from the peculiar clustering of orbits in certain TNOs. These objects, instead of being scattered randomly, seem to align in a way that suggests the gravitational influence of a massive object. This pattern isn't something we'd expect to see without an explanation. Researchers Konstantin Batygin and Mike Brown brought significant attention to the possibility of Planet 9 in 2016, publishing a study that proposed the existence of a planet as the best explanation for these orbital anomalies. Their work has since inspired further investigation and debate. If Planet 9 exists, its gravitational influence would extend far across the outer solar system. It could explain why some TNOs have extremely elongated orbits, looping far out into space before returning closer to the Sun. This hypothetical planet might also be responsible for the tilted orbits of certain objects that don't lie neatly along the plane of the rest of the solar system. The sheer distance involved means that Planet 9 would take thousands of years to complete a single orbit, making its movement slow and its detection incredibly difficult. Finding Planet 9 is a daunting task. Even if it is 10 times the mass of Earth, its location far from the Sun means it would reflect very little sunlight. The planet would be faint, blending into the background of stars and galaxies in the night sky. Astronomers must rely on powerful telescopes, scanning vast areas of space, hoping to spot a dim object moving against the fixed background. It's a search akin to finding a needle in a cosmic haystack. Many distant planets, such as Jupiter and Saturn, radiate more heat than they receive from the Sun due to their internal energy. If Planet 9 lacks this kind of heat signature, it would be even harder to detect with infrared telescopes designed to pick up thermal radiation. Instead, astronomers would need to rely on optical observations, looking for the faint light the planet reflects. The Kuiper Belt is a mysterious region filled with icy bodies, remnants from the early days of the solar system's formation. These objects hold clues about how the planets formed and migrated to their current positions. If Planet 9 exists, it would have played a significant role in shaping the dynamics of this distant region. It might even have influenced the orbits of smaller planets during the solar system's early years. One hypothesis suggests that Planet 9 could be a captured rogue planet, an object that formed elsewhere in the galaxy and was later captured by the Sun's gravity. Rogue planets are thought to be relatively common, ejected from their original systems during violent gravitational interactions. If Planet 9 came from another star system, it would add a fascinating twist to the story of our solar system, showing how interstellar events can shape local dynamics. Another possibility is that Planet 9 formed closer to the Sun and was pushed outward during the chaotic early days of the solar system. The giant planets, Jupiter, Saturn, Uranus, and Neptune, likely underwent significant migration, shifting their positions and scattering smaller objects in the process. If Planet 9 was caught in this gravitational chaos, it might have been flung to its current distant orbit, far beyond the other planets. Despite the intriguing evidence, not all scientists are convinced that Planet 9 exists. Alternative explanations for the observed orbital patterns in TNOs have been proposed. For instance, some researchers suggest that the clustering of orbits could result from the combined gravitational influence of many smaller objects rather than a single large planet. Others point to the possibility that observational biases, limitations in how and where we look for objects in the Kuiper Belt, might create the appearance of clustering where none exists. The search for Planet 9 has sparked numerous discoveries along the way. As astronomers scan the skies, they continue to find new TNOs, expanding our understanding of the outer solar system. These discoveries, while not directly confirming Planet 9, provide valuable data that refine models of the solar system's dynamics. Each new object adds a piece to the puzzle, helping scientists narrow down where Planet 9 might be, or proving that something else entirely is at work. Whether or not Planet 9 is found, the idea of a ghostly giant lurking in the far reaches of the solar system reminds us that even in our own cosmic backyard, there is so much left to explore and understand. The habitable zone myth, redefining Goldilocks planets. The idea of the habitable zone, often called the Goldilocks zone, has been central to the search for alien life for decades. This region around a star is thought to be where conditions are just right for liquid water to exist on a planet's surface, not too hot, not too cold. It's a concept that has guided astronomers in identifying planets that might be capable of supporting life as we know it. But, as our understanding of the universe grows, so does the realization that this notion might be too limited. Life, it seems, could thrive in environments far outside the traditional Goldilocks zone. The habitable zone is based on a simple premise. Water is essential for life, and for water to remain in liquid form, a planet must maintain a certain temperature range. For Earth, this sweet spot is a perfect fit, with its orbit providing the right balance of heat and light from the Sun. Planets closer to their stars risk being scorched, their water boiling away into the atmosphere, while those farther out risk freezing solid, locking water into ice. This straightforward idea has long shaped the way scientists evaluate planets discovered outside our solar system. However, the discovery of diverse environments within our own solar system has begun to challenge the traditional definition of habitability. Take Europa, one of Jupiter's moons. It lies well outside the Sun's habitable zone, yet evidence clearly suggests it harbors a subsurface ocean beneath its icy crust. The heat required to keep this ocean in liquid form doesn't come from sunlight, but from tidal forces generated by Europa's interaction with Jupiter. These forces stretch and compress the moon, creating friction and heat in its interior. This process, known as tidal heating, suggests that a celestial body doesn't need to orbit within the habitable zone to maintain liquid water. Enceladus, a moon of Saturn, provides another striking example. Geysers at its south pole shoot water vapor and organic molecules into space, hinting at the presence of an ocean beneath its frozen surface. Like Europa, Enceladus is warmed by tidal forces, creating an environment where liquid water and the building blocks of life coexist. Such findings force us to consider that moons, not just planets, could be potential homes for life, even in the coldest reaches of the solar system. Exoplanet discoveries have also expanded our perspective. Some planets orbit red dwarf stars, which are smaller and cooler than the Sun. Their habitable zones lie much closer to the star, making these planets subject to intense stellar activity, including flares and radiation. Initially, this led scientists to dismiss them as inhospitable, but new research suggests that planets with strong magnetic fields or thick atmospheres might shield themselves from such dangers, retaining conditions that could support life. This shows that the habitable zone could vary depending on the type of star and the characteristics of the planet. Meanwhile, rogue planets at first glance seem utterly inhospitable, lacking the warmth and light of a nearby star. Yet some theories suggest they could sustain life under the right conditions. A rogue planet with a thick enough atmosphere could trap heat generated by its interior, keeping its surface warm enough for liquid water. Alternatively, subsurface oceans, similar to those on Europa or Enceladus, could exist, protected by layers of ice and heated by the planet's internal energy. The discovery of extremophiles on Earth has also played a key role in reshaping our understanding of habitability. These are organisms that thrive in environments once thought too extreme for life. Boiling hydrothermal vents, acidic lakes, and the crushing pressures of the deep ocean. Their existence proves that life can adapt to a wide range of conditions, far beyond the temperate environments traditionally associated with habitability. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface. It's far too cold for liquid water, but some scientists speculate that life could evolve to use methane as a solvent instead. Such life would be fundamentally different from anything on Earth, relying on entirely distinct biochemistry. Titan challenges the assumption that water is the only liquid capable of supporting life, expanding the possibilities for habitability to include a wider range of chemical environments. Even Venus, long considered Earth's inhospitable twin, has sparked renewed interest. With surface temperatures hot enough to melt lead and an atmosphere thick with carbon dioxide and sulfuric acid, it seems like the last place to look for life. But higher in its atmosphere, where temperatures and pressures are more moderate, scientists have speculated that microbial life could potentially exist, suspended in the clouds. If life can exist in environments as diverse as Europa's icy oceans, Titan's methane lakes, or even the clouds of Venus, then the number of potential habitats in the universe increases dramatically. This means that instead of focusing solely on planets within the Goldilocks zone, scientists must consider a broader range of factors, including a planet or moon's geology, atmosphere, and energy sources. Carbon planets, exotic worlds, rich in diamonds. Imagine a planet where the ground beneath your feet is studded with diamonds, not as rare treasures but as common features of the landscape. Carbon planets are worlds with compositions dominated by carbon rather than silicates and oxygen, representing a fascinating divergence from the geology of Earth-like planets. Carbon planets are theorized to form in regions of space where carbon is more abundant than oxygen. In our solar system, oxygen is far more prevalent, which is why silicate rocks, oxides, and water dominate Earth and its neighbors. But in a system with a different chemical makeup, particularly around stars rich in carbon, the balance shifts. When planets form from the swirling disks of gas and dust around young stars, the relative abundance of elements determines their composition. In carbon-rich systems, planets might coalesce with significant amounts of graphite, carbides, and even diamonds forming in their interiors. Deep within such a planet, where pressures are immense, carbon atoms could crystallize into diamonds, creating vast subterranean layers. If conditions are right, some of these diamonds might even make their way closer to the surface, brought up by volcanic activity or other geological processes. This isn't entirely dissimilar to how diamonds are formed and brought to the surface on Earth, except on a far more massive and exotic scale. Instead of the silicate-based rocks and soils common on Earth, the landscape might feature vast plains of graphite or dark carbides. Depending on the planet's size and temperature, it could also have a thick atmosphere rich in methane or carbon dioxide, giving the sky a hazy, smog-like appearance. Such an atmosphere could trap heat effectively, making these planets hotter than expected, even if they are far from their star. Carbon planets might also have unique geological features shaped by their exotic chemistry. Lava flows, for example, could consist of molten carbides, creating rivers of liquid metal-like compounds that shimmer under alien skies. Mountains could form from layers of diamond and graphite, glinting in the light of a distant sun. The lack of silicates would also mean no quartz or sand as we know it, replaced instead by carbon-rich analogues that would feel alien underfoot. Astronomers rely on indirect methods to infer the composition of exoplanets, often through the light they reflect or absorb. By studying the spectra of light from distant planets, scientists can identify the elements and compounds present in their atmospheres or on their surfaces. In the case of carbon planets, an atmosphere dominated by methane, carbon monoxide, or other carbon-rich gases could provide crucial clues. Additionally, the density of these planets, calculated from their mass and size, might suggest a composition heavier than silicates, but lighter than metal-rich worlds. Some of the best candidates for carbon planets might be found around stars with high carbon-to-oxygen ratios, such as certain types of white dwarfs or metal-rich stars. In these systems, the primordial materials available for planet formation are skewed toward carbon, increasing the likelihood of carbon-dominated worlds. On a carbon-rich planet, life as we know it might struggle to gain a foothold, especially if water, a key ingredient for life, is scarce or locked away in inaccessible forms. However, it's also possible that entirely different forms of life could emerge, adapted to the unique chemistry of these worlds. Instead of water, they might rely on liquid hydrocarbons, such as methane, as a solvent for biochemical processes. In addition to their potential scientific importance, carbon planets capture the imagination with their sheer strangeness. The possibility of diamond-rich interiors or graphite-coated surfaces invites speculation about their appearance and the kinds of geological processes that might occur there. If we ever develop the capability to explore these worlds up close, either with advanced telescopes or robotic probes, they could provide unparalleled insights into planetary diversity and the extremes of geology. How do these worlds form in the first place? And how do their compositions affect their development over billions of years? Do they retain thick atmospheres, or do they lose them to space over time? Are their surfaces static, or are they shaped by dynamic processes like volcanism and tectonics? Answering these questions could shed light on the broader processes that govern planet formation and the factors that lead to such diversity in the universe. Interestingly, the concept of carbon planets is supported by some tantalizing observations. For example, the exoplanet 55 Cancri E, located about 40 light-years away, has been suggested as a possible carbon planet. This super-Earth orbits its star so closely that its surface temperatures are scorching, but its density hints at a composition rich in carbon. While more data is needed to confirm its status, 55 Cancri E is one of the most compelling candidates for a carbon-rich world. Space mining and the future of solar system exploration. Out in space, resources lie untapped, waiting to be discovered and utilized. From rocky asteroids to icy moons, the potential for space mining has been enticing scientists, engineers, and business visionaries for decades. As humanity looks toward a future where we extend our reach beyond Earth, space mining might not just be an ambition, but a necessity. Asteroids are among the primary targets in discussions about space mining. These rocky bodies, remnants from the early solar system, contain an abundance of valuable materials. Many asteroids are rich in metals like nickel, iron, and cobalt, which are essential for construction and manufacturing. Others hold rare metals such as platinum and gold, elements that are scarce on Earth but crucial for high-tech industries. Some even contain water, an invaluable resource for space exploration because it can be split into hydrogen and oxygen to produce rocket fuel or used to support human life. For decades, researchers have speculated about the potential of harvesting materials from space. What has changed in recent years is the technology. Advances in robotics, artificial intelligence, and rocket reusability have made the idea more feasible than ever before. Autonomous mining equipment, capable of operating in the harsh and remote environment of space, could be the key to extracting resources from asteroids. These machines could dig, crush, and process materials on-site, minimizing the need for human intervention and reducing the cost of transporting resources back to Earth. One of the most exciting prospects of asteroid mining is the concept of in situ resource utilization, or ISRU. This approach focuses on using resources in space to support space missions, rather than bringing them back to Earth. For example, mining water ice from an asteroid could provide fuel for spacecraft, enabling longer and more ambitious missions. Similarly, extracting metals could allow for the construction of habitats, spacecraft, or other infrastructure directly in space. By reducing our dependence on Earth-based resources, ISRU could pave the way for a sustainable presence in space. Not all asteroids are equally suited for mining. Scientists classify asteroids into different types based on their composition. Carbonaceous or C-type asteroids are rich in water and organic compounds, making them prime targets for missions focused on supporting life and fuel production. Metallic or M-type asteroids are where precious and industrial metals are found. Silicaceous or S-type asteroids contain a mix of metals and rocky materials, offering a broader range of resources. Identifying and targeting the right asteroid is a critical first step in the mining process. The moons of our solar system also hold incredible potential for resource extraction. Earth's moon, for example, has long been considered a candidate for mining operations. Its surface contains regolith, rich in oxygen, silicon, and other elements that could be extracted and used for construction or life support. More intriguingly, the moon's poles harbor deposits of water ice, discovered in permanently shadowed craters. This ice could be melted into water or converted into fuel, making the moon a natural stepping stone for deeper space exploration. Europa has a surface of ice and a subsurface ocean. While mining its ice for water might be feasible, its potential as a source of biological insight makes it a delicate target, one that would require careful ethical considerations. Titan, Saturn's largest moon, has vast lakes of liquid methane and ethane on its surface, which could serve as energy resources for future missions. Each moon presents unique challenges and opportunities, requiring specialized approaches to exploration and extraction. The economic potential of space mining is staggering. Some estimates suggest that a single asteroid could contain metals worth trillions of dollars. If these resources could be brought back to Earth, they might revolutionize industries and lower the cost of goods that depend on rare or expensive materials. However, this also raises complex economic and legal questions. Flooding the market with cheap metals could disrupt economies and industries on Earth. At the same time, the legal framework for space mining remains underdeveloped, with international agreements like the Outer Space Treaty providing only broad guidelines about the use of extraterrestrial resources. The harsh environment of space, with its extreme temperatures, radiation, and microgravity, presents significant technical and logistical hurdles. Developing equipment that can operate reliably under these conditions is no small feat. Transporting resources back to Earth or between locations in space adds another layer of complexity. Despite these challenges, companies and organizations around the world are investing in technologies to make space mining a reality. Firms like Planetary Resources and Deep Space Industries have been founded with the explicit goal of developing asteroid mining technologies. They envision a future where space mining supports not only exploration, but also economic growth and sustainability. Meanwhile, national space agencies, including NASA and ESA, are conducting research and launching missions that could lay the groundwork for space mining. NASA's OSIRIS-REx mission, for example, has already returned samples from the asteroid Bennu, providing valuable insights into its composition. As Earth's population grows and its resources become increasingly strained, space offers a way to meet the demand for materials and energy. It could also drive technological innovation, creating new industries and opportunities. More importantly, it represents a step toward becoming a multiplanetary species, reducing our vulnerability to existential risks and expanding our horizons. But who has the right to extract and profit from extraterrestrial resources? How do we ensure that space exploration and mining are conducted responsibly, without causing harm to other celestial bodies or disrupting their potential for scientific discovery? These questions require careful thought and international collaboration to ensure that space remains a shared and protected frontier. Jupiter's Great Cold Spot, a chill we don't understand. With its swirling clouds, immense storms, and complex magnetic fields, Jupiter offers no shortage of intriguing phenomena. Among its atmospheric wonders, the Great Red Spot has long been a symbol of Jupiter's volatile weather, a massive storm larger than Earth that has raged for centuries. But there's another feature, discovered much more recently. This is the Great Cold Spot, a frigid region in the planet's upper atmosphere. The Great Cold Spot is not visible in the same way as the Great Red Spot. While the latter is a striking, colorful vortex in the lower atmosphere, the Great Cold Spot resides in Jupiter's thermosphere, the uppermost layer of its atmosphere. It was first observed through infrared imaging, which detects heat rather than light. Unlike the Great Red Spot's warm hues, the Great Cold Spot appears as a cooler region against the otherwise dynamic and hot thermosphere. This temperature difference is striking, with the cold spot being hundreds of degrees cooler than its surroundings. The Great Cold Spot was discovered by researchers analyzing data from Jupiter's auroras. These auroras, caused by charged particles interacting with the planet's powerful magnetic field, produce significant heating in the thermosphere. The Great Cold Spot, however, interrupts this otherwise intense heat with its peculiar chill. Unlike the Great Red Spot, which is a long-lasting feature, the Great Cold Spot is more transient. Observations suggest that it changes shape and size over time, sometimes shrinking to near invisibility and then reappearing later. Scientists believe the spot is connected to the auroras themselves, possibly forming as a result of energy exchanges between the auroras and the atmosphere. The auroras generate waves of energy that ripple through the thermosphere, and these waves may create areas of cooling by redistributing heat and causing local changes in density. While theories link it to auroral activity, its exact mechanisms remain elusive. Auroras on Jupiter are unlike those on Earth. They are driven not by solar wind, but by the planet's rotation and its interactions with its largest moon, Io. Io's intense volcanic activity releases vast amounts of charged particles into space, where they are captured by Jupiter's magnetic field and funneled toward the poles. This creates the brightest auroras in the solar system, bathing Jupiter's poles in ultraviolet light and heating the surrounding atmosphere. How this heating process gives rise to a localized cold region is a question that challenges our understanding of planetary atmospheres. The thermosphere, though less visually striking than the lower atmospheric layers, plays a crucial role in the planet's overall climate and energy balance. Studying features like the Great Cold Spot helps scientists piece together how energy moves through Jupiter's atmosphere, from the surface to space. The Great Red Spot is a massive anticyclone driven by turbulent winds and differences in pressure within Jupiter's lower atmosphere. Its reddish hues come from chemicals like ammonia and ammonium hydrosulfide reacting under the influence of ultraviolet sunlight. The Great Cold Spot, in contrast, has no visual appearance in visible light. It represents a different kind of atmospheric phenomenon, one that is tied to temperature variations and density changes rather than wind and pressure. The relationship between these two spots, if any, is unclear. While they occur in entirely different atmospheric layers, it's possible that deeper atmospheric processes influence both. Jupiter's atmosphere is layered and interconnected, with waves and currents transferring energy between levels. The planet's rapid rotation, strong magnetic field, and immense size create conditions for unique interactions that scientists are only beginning to understand. By studying both features, researchers hope to uncover deeper insights into the forces shaping Jupiter's dynamic environment. Understanding the Great Cold Spot has implications beyond Jupiter. The processes driving the spot might have analogues in other planetary atmospheres, including those of gas giants like Saturn and exoplanets with strong magnetic fields. Learning how energy moves and dissipates in extreme environments could also inform our understanding of stars, which share some physical processes with planetary atmospheres. Wormholes, space-time shortcuts or cosmic illusions. Wormholes represent a hypothetical way to connect two distant points in space-time, creating a shortcut that could drastically reduce travel times across the cosmos. The concept stems from solutions to Einstein's equations of general relativity, and while they remain purely theoretical, their implications stretch the boundaries of our understanding of the universe. The basic idea of a wormhole is rooted in the geometry of space-time itself. General relativity describes space-time as a flexible fabric that can be warped by mass and energy. Massive objects like stars and black holes create curves in this fabric, and gravity is the result of objects following these curves. Wormholes, also known as Einstein-Rosen bridges, are thought to be a kind of tunnel or bridge that connects two separate points in this space-time fabric. If such structures exist, they could allow for instantaneous travel between regions of the universe that are otherwise separated by vast distances. The first formal description of a wormhole came from Albert Einstein and Nathan Rosen in 1935. They were investigating solutions to Einstein's equations that describe black holes, and their work suggested the possibility of a bridge connecting two black holes. This connection was purely theoretical, and Einstein and Rosen themselves did not propose it as a practical method of travel. Their solution described what we now call a non-traversable wormhole, one that would collapse too quickly for anything, even light, to pass through. Theoretical physicist Kip Thorne and his colleagues revisited the idea of wormholes in the late 20th century, considering whether they could be made stable and traversable. For a wormhole to be a useful passageway, it would need to remain open long enough for matter or information to pass through. This presents a significant challenge. The immense gravitational forces near the mouth of a wormhole would tend to cause it to collapse almost immediately. To counteract this, some form of exotic matter with negative energy density would be required. Exotic matter is purely hypothetical and would violate many of the energy conditions we currently understand, but it remains a key ingredient in theories about traversable wormholes. Negative energy density might sound implausible, But quantum field theory allows for the possibility in certain circumstances. For example, the Casimir effect demonstrates that negative energy can exist between two closely spaced metal plates due to quantum fluctuations. However, scaling this effect to the level needed to stabilize a wormhole would be a monumental leap, and scientists are far from understanding how it could be achieved. Even if exotic matter were discovered, there are other significant challenges to creating or using a wormhole. One issue is the potential for extreme tidal forces near the wormhole's throat, the narrowest part of the tunnel. These forces would stretch and compress anything attempting to pass through, potentially destroying it. Another challenge is the problem of causality. Wormholes, if they allow for faster-than-light travel, could lead to paradoxes where events occur out of sequence. This would violate the principle of cause and effect, a cornerstone of our understanding of the universe. Some theories suggest that if one end of a wormhole were accelerated to near light speed and then brought back to rest, it could become a kind of time machine. An observer entering the stationary end could emerge from the accelerated end at an earlier point in time. Many physicists argue that such scenarios are unlikely because they could destabilize the wormhole or lead to inconsistencies in the laws of physics. Despite these challenges, wormholes remain a tantalizing topic of research. They offer a potential solution to one of the greatest obstacles in space exploration: the vast distances between stars and galaxies. Even at the speed of light, traveling to the nearest star system, Alpha Centauri, would take over 4 years. A traversable wormhole could reduce this journey to a matter of moments. For civilizations capable of harnessing such technology, the entire universe could become accessible. If they exist, they would blur the distinction between near and far, present and future. Some scientists have speculated that wormholes might play a role in the fabric of the universe itself. For example, they could be linked to quantum entanglement, the phenomenon where particles separated by great distances exhibit correlated behavior. Some theories propose that tiny, microscopic wormholes might be responsible for these connections, offering a bridge between the realms of quantum mechanics and general relativity. While no direct evidence for wormholes has been found, their existence is not entirely ruled out. Astronomers and physicists continue to search for signs of these elusive structures. One approach is to look for unusual gravitational lensing patterns that might indicate the presence of a wormhole. Gravitational lensing occurs when light from a distant object is bent by the gravity of an intervening massive object, like a star or black hole. A wormhole could create unique lensing effects, such as double images of the same object or distortions that differ from those produced by ordinary gravity. Some speculative ideas even suggest that black holes themselves might be entrances to wormholes. Theoretical models of rotating black holes, known as Kerr black holes, predict the existence of a region called the ring singularity. This region could potentially lead to another point in space-time. However, passing through such a wormhole would require navigating the black hole's event horizon, where the escape velocity exceeds the speed of light. Current understanding suggests that anything crossing this boundary would be trapped, making it unlikely that black holes serve as practical wormhole entrances. The Sachs-Wolf effect, tracing the imprints of the Big Bang. The Sachs-Wolf effect provides a fascinating lens through which we can peer into the earliest moments of the universe's history. Named after Rainer Sachs and Arthur Wolf, who first described it in the 1960s, this phenomenon reveals how the CMB carries with it subtle variations in temperature that can be linked to the early universe's density fluctuations. The CMB has been stretched into the microwave part of the spectrum by the universe's expansion, forming a nearly uniform background that fills all of space. However, it's not perfectly uniform. Tiny temperature differences, on the order of millionths of a degree, appear as ripples in the CMB, providing a map of the universe's early density variations. The Sachs-Wolf effect arises from these ripples. It describes how the gravitational influence of matter in the universe affects the photons of the CMB as they travel toward us. Specifically, the effect has two components, the ordinary Sachs-Wolfe effect and the integrated Sachs-Wolfe effect, each linked to slightly different aspects of gravitational interactions. The ordinary Sachs-Wolfe effect occurs because photons climbing out of gravitational wells, regions of higher density, lose energy, which makes them appear slightly cooler. Conversely, photons falling into gravitational wells gain energy, making them appear slightly warmer. These shifts in energy result in small temperature variations in the CMB that directly correspond to the density fluctuations in the early universe. By studying these variations, scientists can reconstruct a picture of where matter was concentrated and where it was sparse during the universe's infancy. The integrated Sachs-Wolfe effect, on the other hand, is linked to the universe's evolution over time. As the universe expands, the gravitational wells formed by large-scale structures, such as galaxy clusters, can change. If the universe were dominated by matter alone, these wells would remain constant in depth as the expansion progressed. However, dark energy causes gravitational wells to decay over time, which can influence the photons passing through them. As these photons traverse changing wells, they gain or lose energy in a way that contributes to the CMB's temperature variations. This component of the Sachs-Wolfe effect provides crucial evidence for the existence and influence of dark energy. The imprints of the Sachs-Wolfe effect in the CMB serve as a kind of fossil record, offering insights into the universe's earlier structures. These structures were seeded by quantum fluctuations in the primordial universe, magnified during inflation. Inflation stretched these tiny fluctuations across vast cosmic distances, laying the groundwork for the large-scale structures, galaxies, clusters, and superclusters that we observe today. By comparing CMB maps with maps of galaxy distribution, scientists have confirmed that regions of higher CMB temperature often correspond to regions of greater galaxy density, as predicted by the effect. This connection strengthens the idea that the universe's structure today was seeded by the density fluctuations imprinted in the CMB. In a universe dominated by matter, the gravitational wells would remain constant, and no additional temperature variations would be expected. However, the observed data show a slight but measurable correlation between CMB temperature variations and the large-scale structure of the universe, consistent with the idea that dark energy is causing gravitational wells to decay over time. This subtle signal has helped cement dark energy as a cornerstone of modern cosmology. Exotic baryons, unconventional combinations of quarks. While most of the baryons we are familiar with, like protons and neutrons, are made of three quarks in specific configurations, exotic baryons push the boundaries of this simplicity. They involve rare combinations of quarks, or even include heavier, less stable types of quarks, hinting at the universe's rich and intricate subatomic structure. Baryons belong to the family of hadrons, particles made of quarks bound together by the strong nuclear force. In baryons, this means three quarks are tied together by gluons, the carriers of this force. Protons, for instance, consist of two up quarks and one down quark, while neutrons have two down quarks and one up quark. These familiar particles form the building blocks of the atomic nuclei that make up the matter we interact with every day. Exotic baryons, on the other hand, involve quarks in less conventional arrangements. One possibility is baryons containing heavier quarks like strange charm or bottom quarks. These quarks are far more massive than the up and down quarks that dominate ordinary matter. Strange quarks, for example, are found in particles like the lambda baryon, which contains one up, one down, and one strange quark. While the lambda baryon is relatively stable and has been well studied, moving further into heavier quarks like charm and bottom leads to particles with much shorter lifetimes, existing only fleetingly before decaying into lighter particles. The fleeting nature of exotic baryons makes them challenging to study. These particles are typically produced in high-energy environments, such as particle accelerators or cosmic rays interacting with the upper atmosphere. At facilities like the LHC or Fermilab, collisions between particles recreate conditions of immense energy. allowing researchers to momentarily glimpse exotic baryons. Detecting them requires sophisticated instruments capable of tracking their decay products and reconstructing their brief existence. One of the intriguing aspects of exotic baryons is their potential to include quark configurations that defy traditional expectations. For example, while ordinary baryons consist of exactly 3 quarks, some theories propose the existence of pentaquarks, particles made of 4 quarks and 1 antiquark. These exotic combinations represent a significant departure from the standard quark model and challenge physicists to rethink how quarks and gluons interact at the smallest scales. Pentaquarks were long considered a theoretical curiosity until 2015, when researchers at the LHC announced evidence for their existence. This discovery marked a breakthrough in particle physics, as it demonstrated that quarks could combine in ways beyond the familiar 3-quark or quark-antiquark pairs seen in baryons and mesons. The observed pentaquarks included a charm quark and an anti-charm quark, along with 3 lighter quarks, creating a configuration with unique properties. Unlike protons and neutrons, which are stable over long timescales, pentaquarks decay almost instantaneously, breaking apart into other particles. This rapid decay is tied to the immense energy bound up in their quark configurations. Studying their decay pathways provides insight into the strong nuclear force, revealing how energy and mass interplay at the subatomic level. In the first microseconds after the Big Bang, the universe was an extremely hot and dense quark-gluon plasma. Quarks and gluons roamed freely in this primordial state before cooling allowed them to combine into the familiar protons, neutrons, and other particles we see today. Exotic baryons might have been more common in that chaotic environment, playing roles in the universe's evolution. One area where exotic baryons intersect with cosmic phenomena is in the study of neutron stars. The core of a neutron star could be dense enough to support the formation of strange baryons, or even lead to the existence of a quark-gluon plasma. If exotic baryons are present in such environments, they could influence the star's mass, radius, and the behavior of matter under compression, providing astrophysical laboratories for testing particle physics. Some theories propose that dark matter could be composed of exotic particles, including baryons with unusual properties. If such baryons exist, their interactions with ordinary matter would be weak, making them difficult to detect. The search for exotic baryons also advances our understanding of the strong nuclear force itself. This fundamental force governs the behavior of quarks and gluons, holding protons and neutrons together in atomic nuclei. Yet, the mathematical description of the strong force, known as quantum chromodynamics, or QCD, remains one of the most challenging aspects of modern physics. By studying how quarks arrange themselves into exotic baryons, physicists gain insights into QCD in extreme conditions, testing the limits of theoretical models. Exotic baryons might have practical applications, even if they exist only momentarily. High-energy particle experiments often yield unexpected discoveries, and the study of exotic particles has already contributed to advances in technologies like particle detectors and medical imaging. Understanding the behavior of quarks in exotic configurations could lead to new breakthroughs in materials, science, energy storage, or other fields where the properties of matter at fundamental scales become relevant. Every new particle discovered adds a piece to the puzzle of how the universe operates at its most fundamental levels. Whether through pentaquarks, strange baryons, or other configurations yet to be observed, these particles remind us that the subatomic world is far richer and more complex than it might first appear. Wimps versus machos. Competing theories for dark matter. The quest to understand dark matter has long been one of the most profound mysteries in astrophysics. Over the years, 2 primary contenders have emerged to explain what dark matter could be: weakly interacting massive particles, or WIMPs, and massive compact halo objects, known as machos. Each theory offers unique insights into the nature of dark matter, yet both face significant challenges. WIMPs are theoretical particles that are believed to be relatively heavy, with masses far greater than those of protons, and they interact only through the weak nuclear force and gravity. These weak interactions make them difficult to detect directly, but they remain a favored candidate because they naturally arise in many extensions of the standard model of particle physics. In particular, theories like supersymmetry predict particles with the properties of WIMPs. Their hypothetical existence fits neatly within the framework of how the universe evolved after the Big Bang. The appeal of WIMPs lies in their ability to explain the observed distribution of dark matter across the universe. Simulations show that particles with WIMP-like properties would clump together under gravity, forming the vast halos of dark matter that enshroud galaxies and galaxy clusters. These halos play a critical role in holding galaxies together, preventing them from flying apart due to their rapid rotation. WIMP theory has motivated numerous experiments aimed at direct detection. These experiments, often conducted deep underground or in shielded environments, aim to capture rare interactions between WIMPs and ordinary matter. Facilities like the Xenon and Lux Zeppelin experiments use ultrasensitive detectors filled with noble gases like xenon to detect tiny energy deposits caused by a WIMP colliding with a nucleus. Other efforts, such as the LHC, search for WIMPs indirectly by creating conditions that might produce them. Despite decades of effort, however, no WIMPs have been conclusively observed, leaving scientists to question whether they are the right answer. On the other hand, machos offer a completely different perspective on dark matter. Instead of proposing new, undiscovered particles, the macho hypothesis suggests that dark matter consists of ordinary objects that are simply difficult to detect. These could include brown dwarfs, black holes, neutron stars, or even rogue planets. Essentially any massive object that emits little or no light. Machos would populate the outer halos of galaxies, their combined mass providing the gravitational pull necessary to explain the behavior of stars and gas. The macho hypothesis has been tested extensively through techniques like gravitational microlensing. When a macho passes in front of a more distant star, its gravity bends the light from the star, causing a temporary brightening that can be observed. Surveys like the Macho project and the optical gravitational lensing experiment have searched for these telltale signs in regions like the Large Magellanic Cloud. While some microlensing events have been detected, their numbers are far too small to account for the total amount of dark matter inferred from galactic observations. This has led many scientists to conclude that machos cannot explain all of dark matter, though they may still contribute a small fraction. One of the challenges with machos is that they require a specific mass range to work as dark matter candidates. Objects that are too light wouldn't provide enough gravitational pull, while those that are too heavy, like supermassive black holes, are rare and would have been detected through other means. This narrow range makes machos less versatile than WIMPs in explaining dark matter on cosmic scales. WIMPs rely on the existence of new physics beyond the standard model, while machos fit within the framework of known objects and phenomena. The failure to detect either candidate so far has driven researchers to explore more exotic possibilities, such as axions, sterile neutrinos, or even modifications to the laws of gravity themselves. The search for WIMPs has driven the development of more sensitive particle detectors and better methods for background noise reduction, while macho searches have improved techniques in astronomical imaging and data analysis. These tools have applications beyond dark matter, contributing to fields like medical imaging, material science, and observational astronomy. Some researchers have proposed hybrid models that combine elements of WIMPs and machos. For instance, it's possible that dark matter consists of multiple components, with some fraction made up of WIMP-like particles and another composed of macho-like objects. The Cronian phenomenon, unexplained brightness in Saturn's rings. Saturn's rings have long been a symbol of beauty in the night sky, captivating observers with their stunning brightness and intricate structure. These rings are among the most recognizable features of our solar system. However, the extraordinary brightness of Saturn's rings has presented an enduring mystery. Despite billions of years of exposure to cosmic radiation, micrometeoroid impacts, and interactions with other celestial bodies, the rings maintain a level of brilliance that defies expectations. Saturn's rings are composed primarily of water ice, with some dust and rocky material mixed in. Observations suggest that the ice particles making up the rings are unusually clean and reflective. This cleanliness is a key factor in their brightness, as pure ice reflects sunlight more effectively than ice mixed with darker materials. Over time, one would expect the rings to accumulate impurities from the constant bombardment of micrometeoroids and other space debris, gradually dulling their shine. However, the rings' continued brightness suggests that some mechanism is at work to counteract this process, effectively cleaning or replenishing the ice. One theory posits that the rings are relatively young in cosmic terms, perhaps only a few 100 million years old. If this is the case, they might not have had enough time to accumulate significant impurities. This idea is supported by studies indicating that the rings could have formed from the breakup of a large icy moon or a comet that ventured too close to Saturn. Such a recent origin would explain their pristine appearance, as the material would still be relatively fresh. However, not all scientists agree with the idea of a young ring system. Some argue that the rings could be much older, perhaps as ancient as Saturn itself. If the rings are indeed billions of years old, their brightness must be maintained by ongoing processes that actively refresh the ice. One possibility involves the continual grinding of particles within the rings. Collisions between ice particles can break them into smaller fragments, exposing fresh, clean ice surfaces. This process, known as regolith renewal, could help maintain the ring's reflective properties over long periods. While impacts from micrometeoroids are expected to darken the rings over time by depositing dust and organic material, they might also contribute to their brightness under certain conditions. When a micrometeoroid strikes an ice particle at high speed, the impact can vaporize a portion of the ice, creating a temporary plume of vapor that later recondenses into fresh ice. This constant bombardment could act as a natural cleaning mechanism, removing impurities and exposing bright, reflective surfaces. The planet's powerful gravitational field keeps the ring particles confined to a relatively thin, flat plane while also influencing their orbits. These gravitational interactions create waves and ripples within the rings, leading to complex patterns of motion. In some cases, the gravitational pull from Saturn or its moons can cause particles to collide more frequently, enhancing the effects of regolith renewal. Another factor to consider is the influence of Saturn's moons, particularly the small moon Enceladus. Enceladus is known for its geysers, which eject water vapor and ice particles into space. Some of this material eventually makes its way to Saturn's rings, potentially replenishing them with fresh ice. This process could help counteract the effects of micrometeoroid impacts and cosmic radiation. Saturn's rings are divided into several distinct regions, labeled A through G, with varying densities and particle sizes. The densest regions, such as the B ring, are particularly bright because they contain a high concentration of ice particles that scatter sunlight effectively. In contrast, less dense regions like the C ring are dimmer, reflecting their lower particle density and higher proportion of non-icy material. By studying these variations, scientists can gain insights into the processes that shape the rings and maintain their brightness. One of the most surprising discoveries about Saturn's rings came from the Cassini spacecraft, which orbited Saturn from 2004 to 2017. Cassini's observations revealed that the rings are losing material at a faster rate than previously thought. Particles from the rings are being pulled into Saturn's atmosphere by its magnetic field, a process known as ring rain. This loss of material suggests that the rings might be temporary features, destined to fade away over the next 100 million years. If true, the current brightness of the rings could be a fleeting phenomenon, visible only during a brief period in Saturn's history. Which phenomena has fascinated you the most? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.